Hello, and welcome to the very first Cosmos DB conference. We have some awesome content for you today, and we're so excited to have you here with us. My name's Tim Sander, and I'm here with my colleagues Thomas Weiss and Deborah Chen from the Cosmos DB engineering team. I'm going to now turn it over to Thomas to give a quick introduction to the format of the conference.
Thanks, Tim. So here is how it's going to work. This very first remote conference will run as 3 different live streams. We have one stream for the Americas, one for EMEA, and one for Asia Pacific. And each of these live streams will last for 3 hours. We also have an entire track of on-demand sessions that are available right now, but don't go anywhere because we are just about to launch our live stream for the Americas. Now, each of these live streams will have its own unique content delivered by local members of our beloved Cosmos DB community. Now, if you happen to miss any of the live sessions, no stress, don't need to worry because we will make these available on demand shortly after each stream concludes. Now, also good to remember that each of the live sessions we are going to present right now will have a live Q&A with the speakers. So if you would like to ask any question to our speakers, please make sure to join the stream on Learn TV. Deborah?
Thanks, Thomas. As Thomas mentioned, we have a lot of great, exciting speakers and sessions in this 3-hour live stream. We'll hear from customers and members of the community on how they've built their applications on Cosmos DB, how to do real-time migrations into the service, and how to do fundamentals like data modeling and partitioning your data. I'm really excited to introduce our first session and keynote speaker, Kirill Gavrilyuk, Director of
Well, hello everyone, and welcome to our first Cosmos DB conference. We're going to talk about how the world is turning upside down with apps and app patterns changing, and how Cosmos DB helps you sail through these turbulent and exciting times. Let's kind of go back a little bit in time, back a decade maybe, and remember how most of the apps looked largely the same. You had an application, you had an app tier, some API layer, and then the data slowly was dripping to a database. Applications were very reactive. Someone purchased a car, then at some point that this record made it into the database, and probably nothing accessed this record for a while until maybe the next time the person comes to an appointment and we need to fetch some history. Compare this to what's happening today. In the applications, the data is gushing in. It's a river of data that is coming straight to the database. And then applications are moving in and trying to use this data to predict what the customers need. What do the users need? Very different times that require very different databases. Very different scale. Let's walk through what do we need from a database in this new environment. First of all, it needs to scale instantly, transparently, and guarantee speed at any point in time. TCO is very important because the volume of data can change rapidly as we see. We'll have a couple conversations later in this talk, and we'll hear from folks building really exciting and large-scale applications and the scale changes rapidly. The database needs to react instantly. The database needs to be serverless. We don't live anymore in the world where you can think about instances and VMs. We're past that. We need to react and provide performance. Database needs to provide performance and scale when the app needs it, as the granularity that the app needs it. The data changes all the time. It's a river of data. You don't control the river. You don't control the schema. The database needs to be flexible and accommodate any changes in the schema, in the data structure. It needs to make it easy to build these apps that are robust to changes in the data shape. Of course, there are many established, very popular programming models. And the database needs to cater towards developers. Developers are those who are building these apps. They need to build these apps fast. And familiarity with tools and technologies is important. There are great programming models, MongoDB drive and API, Cassandra API, and there are more and more graph databases today. It's important for us to have to offer developers what they're familiar with. Now, the applications are the lifeline of the companies, right? The company does not exist anymore with application. When application even stops working, even for a second, the database needs to be reliable, provide 5.9 SLAs, needs to be resilient to failure. Even if the entire region goes down in the cloud, the application must continue to work. At the same time, applications are also inherently omnipresent. They're everywhere. And so the database needs to be present where the customers are. And so it needs to be globally distributed so that you can bring data where the users are. Finally, applications are in need to ever to close the digital loop, to provide customers timely and predictive services before they know they even need them. And for that, we need to have rich insights in real time, without any delay, without any of this complex ETL complexity. Must be very fast, in real time, provide analytics to drive the app, and provide BI so that the company can react quickly to the changes. Now we have this database. Many of you are using it today. It's called Azure Cosmos DB. It's fast NoSQL database with open API for any scale. Now we'll walk through a few of the updates to where we're taking this database forward. We'll talk to a few folks that use the database today and share their experiences, share their patterns. We continue to double down on serverless. We continue to offer more and more flexibility. We continue to improve the cost profile of the database, making it more and more friendly to developers. We're adding notebook supports. We're offering serverless that we recently announced. We keep in step with the development of the open source APIs for those who are familiar and like the open source APIs. And we continue working to make sure that the database is the backbone of your application. The database never goes down. At the same time, there are some exciting things happening around the real time and closing the digital loop. Let's think about the common pattern today. It's very different from those data drips that we're used to in the past. The data is coming into Cosmos DB straight through ingestion, through Kafka, through Service Bus, through any of the queuing technologies, or directly. The database instantly reacts and autoscales, thanks to the instant autoscales that Cosmos DB provides. Database can instantly react to the volume of data. And then the application is built as a set of microservices. The typical Cosmos DB application is built as a set of microservices that react to the change feed, this real-time interactive transaction logs that Cosmos DB offers to you, so that you can augment and build and develop and enrich your application and close the loop with the user, close the loop with your customers. That's the predominant app pattern today. And let's talk through a few examples. For example, Toyota. Toyota offers predictive analytics. If you're using Toyota, lots of sensors are sending data. The data goes to Cosmos DB. Based on the data, you'll get if you're a Toyota customer, you get predictive outreach and predictive maintenance recommendations in case of something we think is going wrong, before you even face with an issue. But it is not, IoT represents more than 20% of Cosmos DB usage worldwide. But that pattern is not limited to IoT only. If you look at e-commerce, think about an example, and we'll hear from our friends at ASUS later in the day, but think of ASUS example, kind of very simple flow, returns. Returns are going, the signals from the app are going into the database straight, and then the application itself, the logic is is architected as a set of microservices. Each of them knows what to do with particular type of change. Right? So they're all listening on change feed and processing the data, creating materialized views, and sending back the signals and driving the application behaviors. This way, ASS can provide predictive application behaviors to their customers. Now, let me invite on stage Anand Krishnamurthy, Group Engineering Manager from Microsoft Teams. Microsoft Teams does not really need introduction. Many of you use this today. But let's talk about how Microsoft Teams uses Cosmos DB today. Welcome, Anand.
Hello, folks. Thanks a lot for inviting me. It's a pleasure to join all of you. My name is Anand, and I am a Group Engineering Manager for Microsoft Teams, primarily on the messaging side of things, as all of you would use Microsoft Teams. It's been a phenomenal experience, and I want to share a little bit around the same. A few years back, we had prioritized our moving of our legacy store stacks onto Cosmos DB, and that was one of the best decisions we made. We kind of use Cosmos DB, all over all through our messaging services side, our aggregation side, even the transport services actually use Cosmos DB. We're roughly doing about 6-7 petabytes of data. We're doing about close to 2 trillion transactions a second. And the scale that we've been able to achieve with Cosmos DB as our partner was phenomenal, especially given the COVID timeframe. And a lot of people, latched onto Microsoft Teams in order to get the remote work going. When you look at somewhere about, a 2x to 3x growth the first day when we got hit, I think it was March 12th of last year, we just scaled like crazy, and it was amazing to see the decision that we made on the technology stack. Now, we use Cosmos DB pretty much from bottoms up, all kinds of features, all the way from multi-masters to different sets of consistency levels and all forms of replication. Our compliance engines run on Cosmos DB, and so we were pretty we were watching it pretty close, but it was phenomenal to see that over the last year alone, our usage has increased by over 10x. I'm talking about core messaging services. We're talking about billions of messages in a day, billions of meetings that use this infrastructure as well. And so it's been a great experience, moving to Cosmos DB, being able to achieve that level of scale and the kind of reliability, guaranteed 4 nines reliability. And there's a lot of these beautiful reliable features in terms of automatic failover and things that have been helping us, kind of achieve that kind of a transaction model that serves the real-time communication platform.
Thank you, Anand. It's definitely kind of clear from this chart. This is where we're having daily transactions that are going from Teams to Cosmos DB, and we're talking about close to 2.5 trillion transactions per day. And you can see that it changes very rapidly from day to day. Obviously, during the weekends, you have more than 2x dip, as folks thankfully don't work on weekends. And then they come back to work, and the usage comes back through the weekdays. And it changes through the year. There's seasonality. There's obviously a little bit of idle periods. Oh, it's not really idle, but less active during the holidays. How do you guys react to these rapidly changing volumes of data?
This multifaceted approach that we have in terms of reacting to this. There's different models that we follow in terms of what are the total amount of provisioning that's been done. For example, like EDU has become one of our major consumers today. A lot of colleges and school are on Teams, and we've from a Cosmos DB standpoint, we work very closely with some of the teams in Cosmos DB in order to understand the usage patterns, where to optimize and how to optimize it. The one thing that we've been pretty happy about is the scale itself. So from a compute side, yes, we got to go put in some work to build data centers and achieve that scale. But from a storage perspective, we've been able to scale pretty high, even though our throughput, our read and write throughput's been increasing like crazy, over the last year. It's basically a combination of multiple things that we do try to keep up with the current usages.
This is really amazing. Here we're looking at the database of the size of more than 5 petabytes that can take 2.5 trillion transactions per day.
Absolutely.
Amazing. Like, I'm really glad what we were be able to do together, and certainly wish Microsoft Teams nothing more but continuing the 10x growth. This is really exciting.
Thanks, Gil. Yes, absolutely.
Thank you so much, Anand. So as you can see, elasticity and scale are one of the key reasons applications use Cosmos DB. If you just think about 5 petabytes of data, and you continue to use the same database as if nothing changes. Like whether you're using it with just 1 terabyte or whether you're using it with 5 petabytes, it's the same programming model. It scales out the same SDK, same app, and it can react to the changes in transaction volume at ease. Obviously, a lot of work goes behind the scenes into this. Let's look through some of the changes, some of the improvements that we're making to make it even easier for folks to deal with rapid change. Our first, this has been out for a while, but we keep working and tweaking and improving, is instant Autoscale. This is a feature of Cosmos DB where you can configure Cosmos DB on Autoscale, and it will track the volume of your data, the transaction volume, and scale instantly within 10x range, and it will scale asynchronously beyond the 10x range, responding to your traffic. Again, we maintain the same guarantees as when you just provision this throughput manually. We maintain the same guarantees around the throughput, around latency. So you never, if you're using Autoscale, the application does not face with the throttling errors or not enough resources. Wait until I scale. We offer this capacity to your application instantly as it's required, with throughput and availability guarantees. Some of the improvements we're looking at in this area, one of them is ability for folks to do adaptive change to the range of the Autoscale. You don't always need 10x. Sometimes you need less. You actually prefer that we slow down the app a little bit so that you don't, for example, for cost reasons, you don't want to scale beyond certain threshold. So this is coming, and please reach out. We can enroll you in a preview of this. There is work going on at asynchronously and automatically adjusting the range itself of the Autoscale. This is coming. So today you have, when you increase the throughput, when your app needs more than 10x to grow more than 10x, as you've seen with Teams, right? That went through the roof really overnight. Once we all went into quarantine and the kids went to school online, Teams usage went through the roof. They needed to scale out rapidly. And so this is today, it requires going and manually adjusting your Autoscale range and increasing for you through the portal. But in the future, you won't even have to do that. You can just set it on autopilot if you need to. Many other improvements we're looking at in the Autoscale area, how to deal with hot partition keys when in the Autoscale, and how to make it more easier for your application. We also recently introduced serverless. Not everyone may know this. We're using Cosmos DB, but today you have serverless capability available with Cosmos DB. Now, Cosmos DB always was serverless. I mean, there are no servers behind the scenes. You just provision throughput, or you set it to Autoscale and it goes. Serverless capacity mode for Cosmos DB means that you pay per request. So 1 million requests cost 25 cents. If you don't send any requests, you do not pay anything. Similarly, you pay for storage, the same rate, 25 cents per gigabyte. You don't store anything, you don't pay for anything. So it's pure consumption model. You don't pre-provision anything. It's great when you don't know what to expect from the application, when you're just getting started. It's great when you have bursty intermittent traffic that is hard to predict. It's awesome for when you have scenarios that have really low average to peak traffic ratio. It's very economical. It's fantastic for dev test. You don't have to turn off your database anymore when you go on weekends, or worry that you forgot to turn it off. If you don't send traffic, you don't pay. This serverless is available today for all APIs, and we keep tweaking on it. Like we'll keep increasing the limits. Today, not all the features are available for serverless. This will change over time. The intent is to offer all of the database. For example, global distribution today is not available for serverless applications. This will change. We'll increase the storage limit for serverless databases. Many other improvements are coming in for serverless. Stay tuned. Few other exciting since we're all among friends, few other exciting things coming down the road. We are removing a UPGB limit. Some of you may know it, not everyone. It's something when your application really uses Cosmos DB to store a lot of data, but the traffic is not high. In the past, you had to always provision some amount of throughput. That will be gone this spring. And it's actually already, you just need to reach out to us in documentation. There is a link. If you request, we'll remove that limit for you. Pretty exciting about this. So we're expanding the scenarios for Cosmos DB into kind of high storage scenarios. Not everyone runs teams with trillion transactions per day, but lots of very exciting scenarios where maybe you need high throughput, but only for a limited amount of time. Or maybe your throughput is not as high, but your data is really high, really large. We're adding partition key advisor. The choice of partition key is very critical when you use Cosmos DB, and it's important to choose it wisely. And sometimes you don't always can predict the future. So partition key advisor helps you guide how to provide a kind of good future-proof choice of partition key for your application. We're also adding capability called sub-partitioning. This is where you can select, add additional partition keys over time, kind of nested, so that you don't have to. Again, if you discover, there's always a joke among the scale-out systems that when you discover London and New York among your user base, among your partition keys, you have to do something about it. So if you discover a really large partition key, sub-partitioning will help you subdivide it, and so that you can take full advantage of Cosmos DB seamless, transparent partitioning behind the scenes. And we talked about adjustable autoscale range, lots of other improvements coming. Now let's talk about APIs. Cosmos DB is special attention to offering easy-to-use API and programming model. Whether you choose SQL API and can use our drivers, or whether you want to use MongoDB drivers and programming model, or Cassandra programming model, we are there for you. And Cosmos DB API for MongoDB is a very popular API. MongoDB is a very popular programming language. It's a great community. We love MongoDB developers, and we bring all the all the Cosmos DB goodness, this transparent partitioning, a limitless scale, elasticity to the table, offering you through MongoDB API. Now, we recently announced support for MongoDB for all, and we'll follow up with MongoDB 4.2, and we'll continue adding, so keep in steps with the development of MongoDB programming models. Cosmos DB offers wire-compatible API for MongoDB. The nice thing about it is we can transparently offer you both, right? So they might, for example, upgrade from 3.6 to 4.0, should you need it, is transparent. You don't need to bring anything down. There is no kind of rolling upgrade or any of that nonsense. You just turn a button. You turn a button, and 4.0 version is available to you. Some interesting and exciting features. We brought kind of client-driven transaction support to Cosmos DB. We had transaction support in the past, but it required using stored procedures. Not everyone's cup of tea to use kind of stored procedures on the server side. We brought built-in transaction support as part of MongoDB 4.0, and it will be offered across all APIs. We offer the zero downtime upgrade. The binary encoding got really, really efficient. And in fact, if you run using MongoDB 3.6 today with Cosmos DB, we recommend you to upgrade if you can, because you'll get significant improvements from the efficient binary encoding. You may save up to 40% in cost, both on the encodings as well as the RU cost of your query operations and read operations. Of course, if you're using today MongoDB on virtual machines or on premises, it's very easy to migrate. Takes that pain away from you. Focus on the application. We can manage. Cosmos DB is a fully managed database. You don't need to worry about VMs. You don't need to worry about managing the database. There's no concept of DBA with Cosmos DB. It's a database for developers. Developers can focus on the application. We have your back. We take care of it. No matter whether the database grows 10x overnight, it'll be there for you. Just choose the right partition key. Pretty exciting stuff. Let me show you a few demos. So first, I want to show you how easy it is for a MongoDB developer to start with Cosmos DB, right? So you can actually, let's start with whatever we start with. So your other particular search engine of choice. Let's try Cosmos DB. This is a very handy and useful sandbox that you can select. It does not require, you can start working with Cosmos DB without signing up for Azure, without providing your credit card. I want to create MongoDB account. I'm already signed in with Microsoft account, but if I weren't, it would ask me to. Now, it just took seconds, and I now have my free Cosmos DB account. Again, as far as this is concerned, I don't have Azure subscription. I didn't provide any credit card. I just click a button, and it gave me a free Cosmos DB. And it's a very beefy Cosmos DB account. It can give you up to 20,000 RUs for free for a month with limitless renewals. To kick the tires, great environment. 20,000 RUs is a lot. It's like 2,000 or more writes per second, 20,000 reads per second. And we give you portal experience with Cosmos DB. Now, you can't use all of Azure in this portal window just because, well, you don't have Azure subscription, but you can use Cosmos DB and all the features through the portal, and then switch to a proper Azure subscriptions once you feel like this is your cup of tea. So let's create some collection. I can play with it right here in my data explorer. I can go and look. I can create here. I can enable notebooks. A bunch of I can use Mongo shell. I can create new documents right here. Save, etc. Now, but this is a MongoDB database. It's just better, right? It's like I can work with it as a MongoDB database. That's the whole point of it. So let me go to connection string. Let me take this connection string from here, and let me walk over to one of the popular MongoDB tools and connect. Now, Studio 3T is a popular tool out there. There are many others, and you can use any of them. This tool does not know that I'm working with Cosmos DB, okay? Knows nothing about Cosmos DB. But it detected that I have a MongoDB connection string in the clipboard. Said, okay, that's important. Now we can see the URL is actually what we just copied, right? So that's great. Let's test the connection. Again, it just thinks that it's MongoDB out there, and it's excited to talk to it. Awesome. Let's connect to this. And here I have my to-do list collections that I just created. I can go to items. I can see the documents that I added. I can add more documents if needed. I can go back. This is all great. I can go back to my data explorer. I can see that the tools are working as expected. I can look at the, now I have 2 documents. One of them created by 3D Studio. Excellent. Now this is, of course, Hello World. This has been out there for a while. Some of you have, if you use MongoDB API with Cosmos DB, you're familiar with all that. Now, what's exciting is that, let's take a look at another database that I have here. And it's a little bit bigger. Okay, so this one is, let's see, well, it's about 17 terabytes, right? So it takes some effort to set up a 17 terabytes MongoDB database on virtual machines, and good luck doing it on any of the MongoDB services out there. With Cosmos DB, it's a piece of cake. You keep pumping data, whether it's 17 terabytes, whether it's 5 petabytes. What we've seen with Teams, you just keep ingesting data into Cosmos DB. It'll scale out transparently to you, as long as you provide for us a shard key. Now let's go to our connection string. Actually, I think I already have it open here. Yeah, so this is the database I have. I can work with it. Let me go to Data Explorer. I can work with it here, or I can use there's an exciting kind of I can use work with it here, or I can and the data that is stored here is kind of derivative of the popular flights information. Or I can go, and you can see this has all the flights from the Transportation Bureau, and we kind of multiplied it a few times to get to large enough size. Or I can go right here, and I can run a proper aggregation pipeline query against this database. And again, this is kind of 17 terabytes. So if you're running MongoDB on VMs, that may take a while. But with Cosmos DB, that's pretty straightforward. And it will run a little bit, and then it will return back the results. And there you go. Well, this is actually did explain, but my point is that you can aggregate, you can run aggregation queries very fast against any size of data, and that's where kind of the benefits of Cosmos DB transpire, right? So there are a few reasons why folks choose Cosmos DB API from MongoDB. One is that you don't need to worry about manually sharding, kind of creating shards, managing shards. It's automatic and transparent for you. Limitless scale. You can start with a megabyte, and you can get to petabytes of data. In fact, I think the largest MongoDB database we have on Cosmos DB is kind of more than 600 terabytes. Good luck doing it on the native MongoDB engine. It's transparency. Automatic, instant, and granular scaling. This instant autoscale that I talked about, it's a significant. It's mission critical ready. You've seen kind of the critical applications that we all rely on. Whether you're having your kids attend school, whether you're going and ordering a cup of coffee, you buy something in a grocery store, you use Cosmos DB in your daily life. Every one of us, and we rely on it working. And this is the values that Cosmos DB brings, is that the Even if a region, given Azure region goes down, RTO is 0 if you're using Cosmos DB active-active. It's serverless. You don't need to worry about instances. You pay only when you use it. And we'll talk about real-time analytics later in the talk. Now, just few things that we recently announced, advancements to our Cassandra API. This is another API we love. Great developers out there using the Cassandra. We have now a managed instance for Apache Cassandra that helps you build hybrid Cassandra deployments. And you can take Cosmos DB, you can take this managed instance for Apache Cassandra, and you can join an existing Cassandra ring to facilitate migrations. You get flexibility and control. You can take advantage of Cosmos DB serverless, all within your existing Cassandra application without making any changes to it. And you can turn on things like real-time analytics with Synapse Link. Now, with that, let me bring on stage and welcome on stage the person that doesn't really need an introduction, Guillermo Rauch, CEO of Vercel, very well known in developer community. Did many contributions, many modules that we all used in the past.
Yeah,
welcome,
thanks
Guillermo.
for having me.
Excited to have you. Tell us a little more about Vercel. And let me bring up the...
Thanks for bringing up our website. Vercel is a serverless platform for modern front-end focused applications and teams. So customers like TripAdvisor, Patreon, Washington Post, they host and deploy large parts of their online presence on Vercel. They're using modern frameworks like Next.js, which we create and maintain, or others, to create really rich, interactive, and performant front-end experiences for their customers. So when you come to Vercel, we give you this journey of develop, preview, ship. You start with developing, right? So you start with what we call a serverless programming model. When you use a front-end framework like Next.js, we take care of everything that relates to caching, to SEO, to high performance, and we give you a really amazing developer experience. So typically, front-end developers had to choose sort of between like, I'll have a great DX, but I'll give up on SEO, or I'll have a great DX and I'm gonna forego server rendering and other capabilities that allow you to really, really scale your front-end applications. So our customers kind of get this mix of best of both worlds. They get the ability to deploy static applications and they get the ability to deploy highly dynamic, or what we call hybrid applications. So we also power on the preview side of things. Every time you push code, you get a live URL on top of which you can collaborate around the evolution of your front end. So instead of collaborating sort of on top of mockups or a single staging server that everyone fights over, every single deploy you make on Vercel gets this, what we call this preview URL, which we can share around and collaborate with the rest of your team. So to give you a little bit of context of our scale, since November, we've doubled our global edge network traffic to more than 11 billion requests a week from just 5 billion requests a week last November. We 3x'd the number of these deploy previews that we generate. So we see 4 million unique deployments passing through our network every week of teams collaborating on their future front-end projects. And Cosmos DB has been a really big part of our story since the very beginning. So when we set out to create this platform that would, sort of be batteries included for every front end, for every Next.js developer in the world, we kind of decided like look for a database that shared our values and shared our design and our approach to the market as well. So the very first thing that drew us to Cosmos DB was we kind of saw this distinction in the marketplace early even as early as 2017 when we were making this decision of there were databases that were sort of databases as a service. And we also saw that there were services that provided managed databases on top of VMs. And if you sort of zoom out, they look very similar, but there's a very big distinction. And we saw in Cosmos DB that this was a database as a service. It was a serverless approach. It was cloud native, and that would meet our scale. And the number two thing I mentioned, we operate a global network, a global edge network, on top of which we publish your front-end projects. We have our Ingress layer starting in 70 cities worldwide. We generate and cache your pages in 17 regions worldwide. So the global aspects of Cosmos DB were absolutely critical in this mission.
That's amazing, Guillermo. Like, we all run global teams these days, right? And we have, and we all constantly need to collaborate. This is exactly the developer experience that we all aspire to, where every check-in is immediately available in preview to the entire team. Everyone can comment. How do you do this with, you mentioned the global development is an important part of the vision of Vercel, enabling global development. How does Cosmos DB help you there?
Absolutely. So one of the key tenets of Next.js and Vercel is pages have to be very, very, very fast for the end user, right? So I mentioned earlier, sometimes there's been sort of a dichotomy between I have a great developer experience, but I also need my business to succeed at the end of the day. I need my pages to be really, really, really fast. So when you go to a website hosted on the Vercel platform like HashiCorp.com, what happens is we operate an Anycast network that automatically routes you to the nearest location where that website could live. At that point, we try to give developers tools to automatically cache and optimize their websites. So as an example, when you create a Next.js application, we notice all the parts of your app that are static. In fact, we're just looking at a static page within a very large Next.js application, which is Vercel.com itself. This, what you're looking at, is a static. So what happened was you went to Vercel.com in Seattle, we terminated your connection at the nearest edge, and we served this page in a really, really performant manner. So behind all these pages, behind all our capabilities for incremental static generation, for deploy previews, is Cosmos DB providing the metadata layer. So every deploy, every build, every page we pre-render touches Cosmos DB as sort of the central intelligence and control plane of our platform. So instead of depending on manually scaling database instances for something that's so mission critical for us, or having to choose an individual region to host our database, we let Cosmos DB do all the scaling and global replication magic.
That's amazing. Yeah, like, I love this scenario, and we have many these kind of globally distributed control planes kind of built using this kind of, actually, Azure Resource Manager, which is the globally distributed control plane, uses Cosmos DB underneath the covers. All the Azure resources, they're all in Cosmos DB. But I think you guys, because we can evolve together from the very early age, and I admit there were bumpy places on the road. Thank you for
it's been an amazing journey, and as a result, and one of our senior engineers will be giving a presentation. We've collected a lot of valuable lessons that are developer focused, especially for developers that, like us, are part of the JavaScript world in the Node.js ecosystem. If you're curious about how we've scaled with Cosmos DB, the tooling that we've used, the SDKs and layers on top of the SDKs that we've developed, including a Cosmos DB simulator for Node, a Cosmos DB CLI for Node, and a lot of our layers of instrumentation that we've added to connect our observability APM centers with Cosmos DB. You'll learn all of that. Check out Javi Velasco's presentation from the Vercel team.
Thank you so much, Guillermo. Folks, please stay tuned in for Vercel's presentation from Javier. Really awesome, great dev test tools were built along the way. I've used them myself. Vercel has been really awesome partner. Thank you so much. Okay, so can I give just a few words about the one capability that Guillermo mentioned, which is this global distribution, which is a feature that Cosmos DB was born with. It's a cloud-native database built around global distribution. It's not something that was bundled on top. It is part of the core engine, and therefore we are able to achieve very fast replication between regions. Kind of replication happens inline, quickly, in real time, obviously bound by the speed of light, but nevertheless, one of the key attributes of this global distribution is ability to do true active-active deployment, multiple region writes. So application can write into any regions, no failover options needed, and achieve zero RTO. Obviously, to build these applications, you have to account for conflicts. Conflicts may arise when you achieve this zero recovery time objective, when an entire region can go down and your application does not notice. Obviously, the laws of physics, your RPO cannot be zero, but we are working on this feature that brings both of them very close to zero. So you can use strong consistency and achieve close to zero RTO as well. Lots of exciting things happening in the global distribution. I can point you to one example. There is a very nice blog by Walmart engineering team that describes how they moved their e-commerce platform, Walmart.com, one of the largest, over to Cosmos DB with AKS, and how they kind of used that microservices architecture backed by Cosmos DB and achieved the multi-region writes, 5 nines availability, even if there is a regional failure with the cloud, and clouds do have sometimes outages, as much as we don't like it and try to avoid them, application does not notice them. Thanks to that capability of Cosmos DB, the multi-region writes. Check out this blog, really awesome write-up, lots of details around how they did it. Kind of very exciting to see a blog from Walmart.com. Now, I would like to invite on stage another really exciting application. Many of you have used it in the past. Meg Hosinger, key developer behind Yammer Feeds, will join me. Meg, welcome.
Hi, Kirill. Thank you so much for having me.
It's great to have you. Could you tell us a little bit about Yammer? Let me bring you an example of the Yammer feed. Just for
for those of you who don't know, Yammer is basically an enterprise social network. You can see here on this is a typical landing page, this screenshot here. Yeah. So here you can see people are posting, you can reply, comment, like, and we call this a feed in Yammer, and feeds are core to our product. So keep in mind that this is a really high fan out model with a lot of data. And by that, I mean, if we deliver a message, it may need to be delivered to hundreds of thousands of users. And we used to store these feeds in HBase, a self-managed HBase cluster, but we now serve feeds entirely from Cosmos DB.
That's really awesome. What was kind of the most challenging part of kind of building this really high fan out architecture where you need to push these updates to so many users? And how do you do this on Cosmos DB?
Right. So, I mean, I guess I can give a little background of where we came from. We have our own self-managed HBase. We had a really small team managing that. And at the scale that we're operating, it just wasn't manageable anymore. It just wasn't sustainable. We wanted to get out of the business of storing, managing our own storage and build features instead. So that's why we needed a new database solution. And as to how we chose Cosmos DB, I think we had a few key requirements. We have that fan out. We have a ton of data. We have 7 terabytes in Cosmos DB. But what we really needed was something fully managed. We needed something with super low latency, and we wanted something that worked nicely with our Java environment. So obviously Cosmos hits all those buttons. It's fully managed. We trust the Cosmos team with our data. We run in 4 regions and probably more in the future in our production regions. We can add regions with the click of a button. We can fail over with the click of a button. Those are things that we could never do before on HBase. That was a day, couple hours or a day, multiple engineers. And now we just click the button. And we also love Autoscale, as the previous speaker mentioned, because Yammer has sort of ebbs and flows in traffic throughout the day as people come online during business hours. And with Autoscale, we just pay for what we use. It instantly scales for traffic peaks that come through. and we don't have to worry about any of that. Cosmos does it all for us. So the second thing was latency. Coming from our own managed storage system in our in-house, in our same data center, same network, the feeds infrastructure relied on super low latency, and Cosmos ticks that as well with the sub 10 millisecond SLA. And the other thing I mentioned is that we're a Java shop. You think of Microsoft sometimes as like .NET and C#, but Yammer is actually almost entirely Java microservices, and we needed something that would work with our Java structure. And I can attest that the Java v4 SDK is fully mature and definitely production ready. We had some, it was a little rough in the earlier stages, but the current SDK is definitely, go-to and wonderful to work with. And as an added bonus, being on Cosmos DB unlocked a ton of feature development that just was not possible before on HBase. I'm talking things like secondary indexes, allows for filtering and sorting, which we couldn't do before. And it's just, as soon as we got to Cosmos DB, our feature development just exploded because we had so much flexibility with the model. There are more benefits I can go into if we have time too.
That's awesome. I think what we really want to do is we want to set up we'll give a on-demand session and sit down with you and go into details. It's a really exciting use case. Many customers are faced with similar challenges of having the feeds, or they can be feeds, they can be sequences, and solving this large fan out problem where you have to deliver this information to hundreds of thousands and millions of users. We use Yammer every day at Microsoft. It's hundreds of thousands of employees, and we all get them. And it's great that Cosmos DB enables you to ride this wave of growth with ease. Thank you so much. And we'll do a more detailed deep dive on this. Thank you. All right. Well, I wanted to show about one more really exciting feature that we have, and it's somewhat related to the MongoDB demonstrations that I gave earlier, and which is a real-time analytics thanks to with our sister team, Azure Synapse, that we've built together. Now, with Cosmos DB in this new world, right, when the data is gushing into the database and you have to make real-time decisions fast, you have to enable your application to make those real-time decisions to close the loop with the customer. You also have to make some of these decisions you have to make yourself, whether it's to bring more from supply, whether it's to alter, whether it's to react, whether it's to call and reach out to someone. Maybe there is an airbag deployed. You want to be there for your customer in real time. How do you do this? So Cosmos DB offers the real-time rich insights thanks to Synapse Link feature that enable these real-time dashboards, BI, predictive analytics, and it's accessible through the application. The way it works is that we have two stores effectively. We have a transactional store and we have an analytical store. And so as data is coming into the transactional store, it's made automatically available in a columnar Parquet format in the analytical store and offered through Synapse Link to Synapse to any of the runtimes, whether it's Synapse SQL serverless, it's a full T-SQL that you can use to Power BI, or you can directly talk to it as an ODBC, use any ODBC driver, or through the Synapse Spark, and you can build your Spark pipelines, Spark applications, querying this columnar store. And this columnar store is optimized for analytical queries. It's columnar, right? So analytical queries becomes cheap, they become fast. You don't have to build your own ETL pipeline, right? It's all managed by the service for you. If you need to transform the data, of course, you can do it in Synapse, but the data, just to do an analytical query, you don't need to do anything. The data is available to you in real time. The delay is really low, seconds to low minutes between the data hitting transactional store and being available to you in the analytical store. And as you make these analytical queries, they do not impact at all the performance of your transactional store. You don't need to burn or use anymore at all. Obviously, analytical store is much cheaper than transactional, as you would expect. It's 3 cents per gigabyte. It has the queries are cheaper, faster, more efficient, and you don't burn or use on this, which is kind of really valuable. So back in my MongoDB demo, I ran this query, right? This is a MongoDB aggregation query. And if I remove this explain, we'll get more sensible results. It'll give me the kind of average number of flights per month, and few other aggregations on our flights database. And there is a lot of synthetic data in the database, so that it's 17 terabytes, and it ran very fast, right? So I now have my data. I can see how many average per month. Obviously, in 2020, there were much fewer flights than in 2019. Now, what I can do is, if I look at the beacon, we wants to know how is this query so fast, given it's 17 terabytes data. So let me run it again with explain and get back. Okay, so if I look at this here in stages, this is kind of a query plan, if you will, right? You can see that what it did behind the scenes, that it translated into a T-SQL query, and it uses Synapse Link. This is how we achieve the scale, right? You can run this analytical queries. Your application can run these analytical queries over terabytes and petabytes of data. And instead of relying on pegging your operational data store with analytical queries that tend to be heavy, right? And killing it, we use Synapse Link and bring this power to the application, so you can take advantage of the real-time analytics and close the digital loop with the customer. That's an example of the power. This particular capability is coming soon, but this is an example of the power the Synapse Link provides, which we're really excited about. Now, to conclude, lots of exciting things are coming online. I didn't mention lots of security improvements, AD integration, RBAC. We're bringing Cosmos DB emulator to Linux. Cosmos DB is used across the board in many verticals. We just gave you a few examples, and our wonderful guests shared with you their stories of using Cosmos DB and riding this wave of sailing through this world going upside down with the terabytes and petabytes of data rushing to your database with ease, thanks to Cosmos DB scale and performance. Whether you're building apps for retail, manufacturing, financial services, Cosmos DB is there for you. You can read our stories of our customers. You can tune in to our live blogs, and I hope you enjoy our conference. Many more stories are coming. Folks are going to go into a great level of detail about the advancements to Cosmos DB, as well as how they build applications on top of Cosmos DB. Thank you so much, and enjoy the show.
Thank you, Kirill. That was a lot of great content for our viewers, whether they are new Cosmos DB users or seasoned Cosmos DB developers. I think that was a lot of good content to catch up with everything that's happening in the Cosmos DB landscape. We got a lot of great questions in the chat. Unfortunately, we are a bit tight on time, so we won't be able to answer all of them. A quick note for our viewers: some questions haven't been answered because we have kept them for our speaker, but no worries, we will eventually get to answer all of them. Maybe just one, if we have time, Kirill. We have a good question from one of our viewer asking, what is the current status and level of MongoDB compatibility?
With MongoDB 3.6 and 4.0, we achieved very significant. There may be an operator or two that you may find that we don't support, and again, we have all the telemetry, so as folks bring their applications, we're always on the lookout. And if we missed one, we add it right away. We know about it. At the same time, numerous applications are now running. A large portion of Cosmos DB usage are coming from MongoDB API. Pretty significant customers running their Lifeline on MongoDB API. There's quite a few case studies on this effort, and as I mentioned, we have hundreds of terabytes MongoDB databases running on Cosmos DB today. Compatibility is high, but the important part is that it's not just it's a compatible MongoDB database. It's a database that brings you this transparent sharding, painless experience, no pain, no worrying about scale, a limitless scale, instant out of scale, serverless. It's a serverless MongoDB database, something that you cannot find elsewhere.
All right, we are just on time. Tim, do you want to introduce our next speaker?
Yeah, that sounds great. And thank you so much, Kirill, for that awesome session. And it was great to hear, just how easy it is to migrate your MongoDB applications to Azure Cosmos DB's API for MongoDB. And speaking of migration, it's actually what our next session is going to be about. So that question was a great transition to what Alok and Andrew are going to talk about today. And they're going to talk about how to basically migrate in real time to Cosmos DB. So now I'm going to turn it over to Alok to talk about online and real-time database migrations to Azure Cosmos DB with Stream.
Hey everyone, this is Alok and Andrew here. My name's Andrew. I've been working on the Azure Cosmos DB product for about the past 7 years. And over the years, I felt very, very blessed to work with many developers like you. In this session, I'd like to cover one of the most common challenges I frequently see in modernizing applications. And to set some context on this, the common use case I frequently see on why developers choose Cosmos DB over traditional databases is to take advantage of its distributed nature. If you've worked with data at scale before, this is frequently known as the partitioning and replication problem. And Azure Cosmos DB provides the ability to automatically scale out via partitioning, or known as sharding, which enables our applications to remain highly responsive even when they grow to massive scale. In the previous session, Kirill showed us how Microsoft builds applications like Microsoft Teams on Cosmos DB, which allows the underlying data tier to scale to trillions of transactions per day while maintaining latencies measured in single-digit milliseconds. I also frequently see developers leverage the other distributed aspect of Cosmos DB, which is replication, in which we can easily build applications that enjoy a high degree of availability and resiliency. And this is achieved through redundancy by replicating that data live across numerous data centers. Now, a question that I'm frequently asked is, how do I take advantage of Cosmos DB for my existing mission-critical applications? More specifically, how do I facilitate live data movement from my existing legacy database? Can we do this while keeping our applications online and avoid lengthy maintenance periods? What if that data is coming from a traditional relational database? The data model on my relational database tends to be highly normalized, in which we optimize for storage over compute by shredding and joining that data across many tables on each request. But in Cosmos DB, we're taught to revisit how we think about data modeling, which we need to optimize for compute in the form of RUs instead of storage. This is achieved by denormalizing that data, in which relationships are represented through nested objects and arrays instead of joining across tables. Moving from normalized to denormalized data requires quite a bit of data transformation. Can we do this as part of our live data movement process? So to solve this problem, I've had the great pleasure of working with a very, very good friend of mine, Alok, who is the founder and chief product officer at Stream. Stream built some amazing tooling that targets solving this very specific pain point. So Alok, it's very, very nice to have you with us. Would you like to tell us more on this?
Sure, absolutely. Thank you so much, Andrew, and thanks a lot. Hope everyone's enjoying this virtual Cosmos DB conference. I'm really delighted to be part of this. And let me pick it off from where Kirill and Andrew left off. And so in this session, in the next 30 minutes, I'm going to be talking about primarily the data movement and the data migration problem that was just touched on. I'm going to start off with a platform overview. So that's going to give you some idea about the feature functional capabilities of what can be achieved and how to set up the actual migration and the integration data pipelines. And I'm also going to point out some of the challenges along the way, as it comes to both the denormalization, moving data from your legacy systems onto Cosmos DB. How do you do mapping between different, for example, from one primary key to a partition key? How do you scale the workloads and so forth? And I'm going to wrap up and I'm going to try to show you a couple of demos. Hopefully, I'll have time to show you both. So with that, let's get started. So first about Stream. So Stream as a partner, and we've been working with Cosmos DB for several years. So we enable continuous enterprise data movement to the cloud. And the core idea is that you might have a number of different applications running against different types of database systems, NoSQL systems. Many of them could be running on-premise. They could be running in other clouds. And oftentimes, to sort of take advantage of the very low latency access in a distributed fashion for the Cosmos DB workloads, you want to move the data into Cosmos DB. So what we do is we facilitate that. And the core focus that we have in line with why you want to deploy a lot of these applications on Cosmos DB is the real-time aspect of it. Now, if you sort of take a look at the picture to the right and take a look at data as an iceberg, there's ways to come at the data directly through the APIs of the application and then move that onto, let's say, a system like Cosmos DB. But oftentimes, when the data volumes are super high, and we're really talking about tens to hundreds of thousands of events per second in a traditional legacy database, then how do you actually come at it from an API that's at the application level? That becomes a critical challenge. So oftentimes what people do is they tend to come at it more in a batch basis. And what that does is it introduces latency between the traditional system and Cosmos DB. And that's one of the things you're trying to avoid because of the sensitive nature in terms of low latency for many of these applications. So one of the sort of the revolutionary techniques here is something called chain data capture and the ability to stream in a very non-intrusive fashion data from many of these systems into Cosmos DB. So I'm going to spend a significant amount of time getting into that area today. Okay, so just overall to set the stage as to how the pipelines would work, and as developers, how are you guys able to work with Stream as a platform to ultimately work with any one of the APIs for Cosmos DB, any one of the different models, and then stream the data there? Let me just set up the high-level picture. So you have a lot of different applications that you're running today. They could be running on databases. There could be some applications that are generating log files or writing data to messaging systems, which could be, for example, Kafka. And data could also be coming in over different protocols, let's say TCP, UDP, HTTP, etc. So within the platform, the entire orientation of building a pipeline is having a drag and drop type of an interface. And then at the back end, there's Java code that actually gets executed for continuous data collection. And at a very straightforward type of a pipeline, you can continuously collect this, and you can actually deliver this into different collections onto Cosmos DB, into different containers. More interestingly, as you start moving this data, Andrew talked about some of the challenges that come along. You might have, very normalized data, and then you want to sort of split that up and write different portions of that data to different containers. Or you want to coalesce it sometimes so that you can bring it together into one container so that you can have denormalized access to that data for your applications that are running on Cosmos DB. So one of the things that you can do is as the data comes in, you can either event by event or on a state like a little window, which is temporal, or it could be batch based. You can hold that data, and this is all happening in memory, and you're able to apply a number of different transformations or aggregations or enrichment, or even join this with data that is reference data. And this is one of the critical requirements that often come, we face as developers, where we want to move the data to sort of, create the overall document as we move the data. So in this example, you can see that logically you are able to not only transform the data that's coming in, you can also, massage it using an external context. So you could preload data from additional sources into the Stream platform. And now you can literally join that data, as you take that data. This might be, for example, for enrichment of that data. Some more advanced capabilities might be there are operators. One thing I should have mentioned is that a lot of the capability is through the UI. So you are able to actually, and I'm going to show you that later, you're able to take a lot of the operators that we have and apply that on the record itself or on the window. And if you wanted to extend it, you're also able to write your own queries in SQL, or if you wanted to do some advanced integration with your own machine learning models, for example, because the model might want to give you a value that you want to store as part of that data, then you're able to also write your own Java code, and you can actually link in with that. Along the pipeline, so again, just stressing on the collection piece of it, the transformation piece of it, and the transformation could involve multiple different tables, for example, coming in from an Oracle database or a SQL Server database, MySQL database, and you can actually massage it, or you could split it apart and then give that as different event streams to the platform, and each event stream could then be talking to a different container. And we'll get into the guts of that. I'm just trying to set up the high-level picture here. Along the way, there's a lot of operational monitoring. So there's a lot of debugging capabilities that you can take a look at the kind of the image of the data that's coming in. And once you actually apply the transformation operator, there's also a post view of that record. So let's say if you have a record that's coming in, which is a straightforward tuple from a relational database, you can actually convert that to a JSON object, and you're able to actually visualize the JSON object along the way prior to delivering that over the API on the Cosmos DB side. Okay. So let me just quickly get into why is this interesting, and where do we see a lot of our joint customers who have these development teams struggle, and what are the challenges they're trying to solve. So I think some of them were mentioned. Obviously, you might actually be trying to sunset an application that may be running, let's say, in a legacy database like Oracle. You might actually have data coming in from a NoSQL system like MongoDB, and you wanted to do a migration and eventually phase that application to Cosmos DB. You may want to do data denormalization, like I mentioned, where it's not your goal may not be to sunset an application, but there's a new application that's being deployed to kind of do digital transformation or data modernization, and as part of that, you want to sort of have a brand new application run on Cosmos DB. Real-time telemetry and event feeds into Cosmos DB. That's another critical use case, and this has to do with the ability to ingest at very, very high volumes. So typically millions of events per second, if that's the kind of use case that you have. Doing parallel reads, if you have a Kafka cluster and there's a large number of partitions, then how do you actually go in and do continuous data collection across the Kafka topic, which may have hundreds of partitions, using a very simple pipeline that allows you to capture the data continuously and then move it to the Cosmos DB target system. And lastly, even if you have just normal JSON data that's coming in from some application in a file, or maybe over some network protocol, then you can actually take those and then also move that onto the Cosmos DB side. So these are sort of what I call the use cases, if you will, which are meant to be addressed. Of course, we are focusing today on the migration and the data movement, which is very real time, so that you can ultimately you have maybe let's say an Oracle system running. You set up your Cosmos DB system, and then you sort of sync them up, and ultimately you're going to pull the plug and then just have a new application running on the Cosmos DB side. Okay, so let me just quickly get to how is this actually done. So typically the objective is, hey, I want to migrate some existing tables or collections, let's say from Mongo, with an intent to cut over to the Cosmos DB database. And the idea really is that, hey, I may want to just completely migrate or keep the two sides in sync. And along the way, there's these transformation and, let's say, denormalization capabilities that I want to actually introduce. So typically, there are two things going on here. One of them is, how do I do sort of like a scaled instantiation, or often known as an initial load, where you might have existing data for a decade or 2 decades, and you want to now move all of that data over. So you kind of have an initial snapshot. And the other aspect of this is, well, what happens, because you can't really take downtime, so the data is actually changing on your source system. So how do you accommodate for that data? And that's is the synchronization phase, right? That accommodates for your ongoing changes. So within this synchronization, there's a couple of things that you face, as when you're developing these pipelines. Number one is, how do I keep it real time? Because like I mentioned, if you're going to go take a batch-based approach, then oftentimes you don't want to impact the source database, which is running a mission-critical workload. So you're going to add a lot of impact and overhead if you're constantly pulling that the system to detect for any delta changes. So that turns out to be a non-starter typically. Number two is you do want to have some sort of a high-speed interface, and that's really what oftentimes people want to use an interface like CDC, which is a change data capture interface. And many of these systems allow you to have an API where you can mine the transaction log or the redo log, or maybe the ops log, and then you can actually take the changes from there. That turns out to be one of the most efficient ways in which you could grab the event stream for applying on the target system. The other part is that you want to make sure that you're able to keep the two sides in sync, which means that not only are you collecting the data, you're also applying it using the APIs on the Cosmos DB side, and you have to be able to parallelize that the writes to different containers. So you want to make sure that you're able to keep up in near real time between the two systems, so that ultimately you can actually fail over or cut over to the Cosmos DB side. Okay, so these are kind of some of the synchronization challenges. So let me just talk about what is the big deal here. Why what is the complexity here? So oftentimes, right, people are not going to allow you to put triggers on the source system, because that turns out to be just super expensive on a critical application that's running on that database system. So the problem with the log records is you're not writing them as you're applying records to a table. Typically, these are very compact binary representations of the change vectors that you produce against data blocks on the actual tables, which are represented and coded as redo records in the transaction log. So that structure, you need to interpret that, and then you need to be able to map that onto the model on the Cosmos DB side. And that turns out to be challenging. You have to write a lot of code, you have to understand the format, and that's not that simple. Oftentimes, you might do things like partial updates. So if you do a partial update, then what happens if you already have a complete image of that document in Cosmos DB, and now someone just updated, let's say, on the source system, just 2 of the columns out of the 100 columns, well, then the document that I construct might be a partial document. So how do I deal with things like that, right? So these are the things that you need to pay attention to. If there are failures along the way, then what are the event guarantees in the change data stream? Am I able to pick up things from where I left off, or do I have to worry about writing the logic to figure out where things are? So these are again some of the complexities that come in as you're trying to handle the change data records. One also very interesting thing is that many of the underlying databases may not give you the changes in a transaction commit order. So they might actually be writing the records in an interleaved fashion in the redo log. So, and then ultimately the transaction possibly could even roll back. So if you're mining the changes in real time, then you also need to assemble them so that you may have like a complete transaction. And then you need to map this transaction. For example, if it goes across an orders table, and then also like a line item table, then you want to have that be represented in maybe one document. So then you need to strip out portions of the values from those records, and then create a document and then move them forward. Okay, so these are sort of some of the interesting things that come up as you're dealing with CDC in your pipelines. So in Stream, how do you do this thing? So my next few slides are going to talk about that. So what we've done is we've sort of given a visual environment where there are pre-built wizards. So you can see that there's wizards from MongoDB to Cosmos DB and Oracle CDC to Cosmos DB, Microsoft SQL Server, and there's really a lot of the popular sources that you want to develop for. So the idea is that you're starting off with saying, here's my source, and then you're able to write, as developers, either you can take our pre-built functions and apply those to the pipeline, or you're welcome to write your own in SQL or in Java. If let's say I mentioned, if the out of the box function is not satisfactory and you really want to invent your own interesting algorithm to maybe massage the data. Oftentimes that may be required, particularly if you are denormalizing the data across multiple different sources, because it might require custom logic. So you pick one of these wizards, and the way this thing happens is in 3 high-level steps. And I'm going to show you the demo as well. So you select the source. So out of the box, you can actually select a number of different sources like Oracle or MongoDB or MySQL or Postgres or Kafka, etc. So in this case, I've selected maybe the Oracle reader, which is getting my inventory data. And then there's a designer palette which allows you to say, hey, am I trying to transform an event that's a normal event coming from a file, or is it coming from a database? So the database event allows you to deal with the CDC record that I mentioned earlier. Because remember, that is not specific to a single table. So its schema doesn't conform to just one type. You might have changes to hundreds of tables, but they're all being represented as one logical change record. So we have operators that allow you to massage that data in that logical change record based on these database event transformers. So you can actually add your own custom fields. You can modify the data. You can add your own metadata if you wanted to, oftentimes, because sometimes we've seen cases where there may not be a good partition key. So you want us to add your own key along with the data record, so that on the Cosmos DB side, we're able to be super efficient and get to the right partition and identify the subsequent record. Okay, and step 3 is there's a writer piece of it. So far there's a reader, there's like this transformation capability, and this is a very linear, simple graph. You could actually, the middle tier here could have like 10 different components, and you could have a kind of a fan-in model back into a data stream, which is then talking to the Cosmos DB writer, which is another component within the stream platform, and that's the one that actually leverages all of the APIs to then finally deliver the data onto the Cosmos DB side. Okay, so with this, this is sort of like how you set up the configuration of the pipeline itself. And there's like a lot of useful functions there that you might want. For example, if you want to do some aggregations, or if you want to do split records or mask records, you can do stuff like that. We do support all of the popular APIs that Kirill talked about earlier. So if you're familiar with the core SQL API or the Mongo API, Cassandra API, we support all those APIs. These are within the Cosmos DB writer, okay, for stream. So the incoming data format, this is an interesting point. I think I talked about this briefly. So the incoming type could just be a straightforward record that's coming from a table. It could be coming in from the actual transaction log. So in this case, you can see that not only do you have the data, but you also have the metadata, things like the table names and the redo byte address where the record was generated, and the system commit number, all those things that the transaction log keeps track of. If the data is coming in from MongoDB, then again you could have just the document itself, which is coming from the collection, or you could have the ops log record, which again has the data and the metadata. And these are just for your convenience, because if sometimes you may want to add some metadata as part of your collection, before you apply to the container on Cosmos. And finally, it could be just coming in as straight through JSON documents from a file or from Kafka. Okay. So I think we have about 7 more minutes, so I'm going to speed up. These are my last couple of slides before I get to the demo. So the idea in Cosmos DB Writer, which is the main component, which is leveraging the APIs, are we receive the data from the data sources. That's coming in as an event stream. You can join that with the data preloaded from a cache in stream. There's a data structure like that. Or we can even do lookups to an external system. Let's say over an API like JDBC, grab that, and then you can actually go ahead and apply that. Supporting and writing different tables to different containers is supported. We can replay inserts, updates, deletes that are coming in from the source side. And mapping is just supported pretty much out of the box. There is advanced capability. So if you wanted to map specific columns to specific fields, then you're able to do that as well. Finally, just from a scale point of view, Stream can run as a cluster. So it can scale up with similar to Cosmos DB. Literally, we're moving billions of records over a day at many of the retail sites worldwide. And we do take advantage of batch optimizations in all of the APIs for the various models that I mentioned earlier. Okay, so with that, I'm going to give you a demo. I have about 6 minutes. So let's actually step into the Oracle to Cosmos DB demo first. Okay. Perfect. So this is a recorded demo, so I have the luxury of actually pausing and highlighting some interesting things that you might be interested in. And of course, please feel free to send questions as you dig deeper into this thing. So this is so there is a web server as part of Stream, and we're just connecting through the UI. The apps represent the pipelines. So I'm going to step into the apps, and here you can see that there are 2 pre-built pipelines. One of them is called Aura to Cosmos. The other is CDC Azure Monitor app. Okay, so let's step into the Aura to Cosmos app. Okay, so once I step into the flow, let me just pause this. You're seeing top to bottom a graph, and this is how the data flows from the data source into the small component with the squiggly lines. That's a stream. So the stream is sort of where each one of the records comes in. And then there's another component, which is enrich CQ. That's a continuous query that's constantly and continuously enriching the event that's coming in. And then it's going to go write it to 2 ways, one to Azure Blob Storage and the other to Cosmos DB. Okay, so, and the way this is built is by doing a drag and drop from the components on the left side, where we have support for lots of different sources to talk to your Cosmos DB target. Okay, that's how this graph itself was generated. Okay, here's the operators that I was talking about earlier. So let's step into, this is the configuration panel on the right side. Here's where you can actually say, hey, what are the tables that I'm interested in moving live to Cosmos DB? In this case, I mentioned earlier that you can enrich your data. So at the top, if you take a look at the Oracle Reader, that was where that's the connection to the database. The other one is this sales rep cache. So we have some preloaded data from, in this case, just let's say a file, and you can actually join across these 2 based on the rep ID, the sales rep ID, because the name may not be available, and we want to push the name into the record. So this is an example of how you can actually, denormalize some of the data, and then and I'll show you the query as well in just 1 second. Okay, so this is currently we're looking at the cache definition here. Let's take a look at the query that does the join here. So you can see that I'm just writing a simple select statement across my Oracle source as well as the sales rep cache, and then I'm joining that on the rep ID so that we can pull up the rep name. Okay. And then let's just go forward a little bit on the targets. I'm going to jump into the Cosmos DB side. That's where you provide your access keys, etc., and the mapping capabilities on the Cosmos DB. Let's go ahead and deploy this application. And once I deploy it, I'm going to start it. The start of the application is what gets the data flowing. I had mentioned earlier that you can actually preview the data. So in this case, once the source starts feeding the data, you can actually start previewing, and you're seeing the actual, the records that are coming in. And you can see that I pulled in the sales rep name as well from the cache. So far we're getting this data and we're previewing it. We're going to then take this data, and then depending on which API I'm using, it's going to actually go ahead and format that and push that on the Cosmos DB side. So let's take a look at that. Okay, so here's I'm logged into the Cosmos DB database, and you can see that the specific orders and the items are available now on the Cosmos DB side. Okay, and the similar to this, I showed you the Oracle demo. We have about a minute. There's a lot of monitoring capability here. The key, I'm going to skip past some of this stuff to get to the interesting pieces that you as developers might be concerned with. So you want to often see what is the resource usage. Is my data on an aggregate basis? Let's say I'm moving so many events per second. What is the rate at which I'm applying it to Cosmos DB? So that you can scale into parallel flows. A lot of that capability so you can configure and scale the Stream platform along with how many containers you're writing to, and also on the depending on the data that's available from your source, depending on the throughput that you're receiving there. So I'm going to stop there. I don't think I have time to get into the second part of the demo, which is the MongoDB reader. It's very similar. Let me just give room for just maybe a quick question or two if we have the time, because it's about 10:29. If you do have any other questions and comments, you can go to our website at stream.com, or you can also go to the Azure Marketplace and just take it for a spin. So both options are available. And with that, I'm going to take any questions that might be there. Thank you.
Thanks, Alok and Andrew. Actually, we are a bit short on time again, but we will take any questions we had offline, and we'll get your help to answer the questions we had. Thanks. That was, again, great content, and hopefully it makes it a little bit more obvious for our users to understand how to migrate data to Cosmos DB with Stream. So again, we are right on time, so let's move to our next speaker. And next up, we have Sandeep Nawate from Adobe, who is going to share his experience in creating a unified view from multiple data sources, which I think is something that would resonate with many of our viewers today, because more and more we need to combine multiple data services together, and this can prove to be a challenge to operate. On to you, Sandeep. Take it away.
Thank you. Thank you very much. I want to start with my thanks to Microsoft team here for giving me this opportunity to talk to all of you guys, as well as all the viewers who are tuning in to this particular presentation. I'm Sandeep Nawate. I run engineering for Adobe's Experience Platform. I will be talking about what we're calling unified profile and identity architecture for Adobe's Experience Platform. There's a lot of work we have done over the last 3-4 years at a fairly large scale system that has been built. And it's heavily using right now Cosmos DB as well as many of the Azure technologies. So I'll be actually walking you through that. The agenda today, I will actually firstly introduce you to Adobe's Experience Cloud, position of Experience Platform within that, and the next layer down below that is where the profile and identity structures actually emerge, and the importance of these structures in the customer era, as well, actually getting into the architecture, some of the issues that we actually saw that we're trying to solve, talk about the scale that we are achieving with the underlying technologies that we're using. Okay, so let's look at the Adobe's Experience Cloud. Okay, as a whole, Experience Cloud applications are known in terms of, let's say, Analytics Cloud at the topmost layer here, which is Analytics, Audience Manager, which is a DMP solution. You have Marketing Cloud, which has solutions such as Campaign, which is email marketing solution, Marketo, B2B related marketing solution, Engage, Target, Experience Manager. You have Commerce solutions, which are Magento. All these solutions are essentially known as an application layer. Right below this, you see the entire layer, which is the application services and the platform layer. Adobe's Experience Platform is something that was conceived over the last 4 years, and we've been working on it for the last 4 years. Today, it's large-scale platform available as a product and selling in the marketplace. It consists of some important components such as real-time customer profile. This is going to be our focus area of discussion today. There's a lot of AI machine learning techniques that are actually getting used. This entire platform is built with the thinking of an open ecosystem, extensible data model, as well as complete microservices-based architecture. Now, the entire system has been built on top of cloud. There are application services built, and this entire stack together is becoming the new generation of Adobe's Experience Cloud. Okay, now when we started looking at building Experience Cloud, the question was, okay, how we are looking at different challenges that marketers are actually facing. So let's look at the marketers' challenges that we're trying to kind of solve. If you start looking at the experience era, okay, the problem that we're looking at for solving the customer experience is that in the modern world today, every single thing gets driven out of how an enterprise is interacting with consumers. Their experience, their actually decides the long-term loyalty. And this is the long-term value that we're trying to go after. Now, to understand actually building this loyalty and providing the best experience, most important thing for a marketer is you must understand your consumer first. You must understand your customers completely. Okay, this is the 360 view of your customer that you need. A comprehensive view of your consumers or the customers is important. And it's not sufficient to simply say that I'm going to just take all this data coming from enterprise systems as well as interaction systems laid it down in the data lake. That's not sufficient. So that becomes one of the important challenges. Next part is that as you start figuring out how to bring this data, the new world of activation, which is the word activation actually refers to how do you take this data and take actions to provide the experience to the consumer. This activation is more or less happening real time. Today's scenarios is 100 milliseconds to 250 milliseconds is becoming more or less the norm in the industry, saying we must respond in this particular thing. And we will look at some of the use cases there. Now, this becomes the second challenge. The next one actually gets down to saying that it's not just about being real time, it's real time across every single channel that the customer is present. The channel here means your phone, your tablet, your laptop. All these are digital devices. A consumer or a customer could be present anywhere, and you must provide experience that is actually orchestrated well, which is understanding the user's behavior across all these channels, and providing experience becomes important. Now, this scale of data, if I try to bring together, I run into the next challenge, which is, hey, there is privacy regulations that are actually there everywhere. User consent starts important thing. I need to start thinking about the GDPR and related CCPA, these kind of regulations that are actually coming into play. So you need also a governance framework around this. So these were some of the kind of important challenges for the experience maker that we were looking at. And from this, we started looking at saying we need to build the experience platform. So let's look at the experience platform architecture at a high level. This is more like a architecture view. Okay. From the left-hand side, what I have is I have data sources that are trying to bring in the data. The data sources essentially are data such as interactional data. Interactional data is what happens on the web, what happens actually in your mobile devices, what happens, let's say transactional data. This could be coming from e-commerce, could be coming from brick and mortar, right? Operational data, the third-party data set, all these data is arriving in the system. Today's world, the data is coming more or less moving into everything becoming streaming. Just-in-time data arrives and you're expected to take actions on it. But batch data still lives. This data, as it arrives in the system, next part is building essentially a data model. The system is built with a thinking that it's an extensible data model, more or less feels like a JSON structure with a schema. Okay, and we call it XDM, or the experience data model. This data model is flexible, where any customer can adapt to their business needs, and we actually take all this data and convert. There's ETL processes as well as mapping that happens in real time, and data gets collected. The data gets laid down in data lake for certain purposes, as well starts moving into the next leg, which is the building the real-time customer profile. The profile building exercise has two different aspects to it. One is the profile and identity, and we separate the two things out, and I'll get into details of why the separation is needed. And both of these components heavily depend upon using Cosmos DB, and I'll actually talking about that. Then the part is that what kind of workloads the system actually starts supporting, which is profile lookup, segmentation, batch segmentation, real-time segmentation. There are many workloads that actually system needs to start supporting. This data goes to the next leg, where we want to start building insights. So using the data lake, as well as using all the assets that are being laid down within Cosmos DB, we start looking at how I can start bringing insights. Insights come in terms of running simply queries, analytical and BI workloads, running data science, model operationalization kind of aspects. All these things bring together insights. Now what I have is I have profile, which is unified. I have insights, and now I take it to my activation points. Activation points is where I deliver my experience. This is where edge computing and many of these things start coming into play. And in the modern era, it's not just that I'm actually just taking the data there and taking actions. Streaming services require actually doing processing of the queries as events actually arrive, looking up the data from the profile and acting on it, and then delivering actually the experience to the customer right on the time. Okay, let's get to the next level of details with respect to profile and identity, and why this is actually becoming important, okay, for the marketing use cases as well as reporting use cases. So in the marketing, I think many of you guys are already aware, marketing use cases come out in many different ways. There is definitely personalization that is actually happening in web and mobile and in-app and all these things, which is what I look at a personalization systems is that an incoming request, it's actually segmented. All the audience is segmented into a large set of users. And that set sees more or less the same exact experience. That is generally called a personalization. Now, set size can vary, but we have seen set sizes getting into 10 million to 100 million users falling into a single set, which is essentially you're not doing much personalization. Okay, as you get this set smaller and smaller, personalization actually goes higher and higher. Now, this is happening today, whether it's happening in the email marketing, it's happening in push notifications, or it's happening on the inbound channels. Interaction is kind of a new kind of thing. If I were to say that personalization is actually unimodal, it's either inbound or it is outbound, but it's not both at the same time. Interaction is bimodal. And we are seeing a whole lot of interaction that is happening. And I'll tell you a few examples of what interaction actually means. Interaction has one more characteristics. It is about one individual. So it becomes personalization to the next level, which is a segment size of one or fully individualized. Where do you see interactions? My most recent experience actually walking into DMV was very, very thrilling. You know that in DMV, you will just completely waste your time just actually standing in lines. This was a situation where everything happened completely with devices, where I was not standing anywhere physically in line. My actual work within DME was 5 minutes, walk to the counter, get the job done, get out. Everything happened through devices. And there was a continuous interaction from my phone into the system, starting initially from my browser, then from the phone, and everything actually worked out. Now, this is happening in government offices. I've seen this in libraries. Library checkouts are actually changed. You're seeing this happening in enterprises. You're seeing this happening in retail, right? Buying online and picking up in store is one of those interactional examples we are actually seeing. You're seeing that happening in the food industry. You're seeing in hospitals. So you're seeing this happening pretty much everywhere. And COVID environment has pushed it into high gear. And much of this requires almost instantaneous response. You cannot wait. So these are becoming two dominant examples. The next example is really reporting, which is where you're trying to kind of, reporting is kind of a broader title, but really pulling analytics together, BI, attribution. These are kind of use cases which require full understanding of single consumer or a customer and their identities. Now let's look at the details of the problems with respect to identities and profile. So here is kind of the view of the world I'm going to kind of talk about. Let's consider this is my picture, a poorly drawn picture of Sandeep, okay, the consumer. You are essentially looking at his interactions actually in all different devices and different places. You have essentially a phone, you have a tablet, you have a computer that you're interacting with. There's a brick and mortar interaction. He's talking to a customer service representative. Every single place, there is an identity. There's a primary key. If you were to think about database people like us, right? There is a primary key that we are actually talking about. And this primary key essentially is like IDFA, the cookie actually, or the CRM ID. These identities exist. And each one is different, okay? Now let's look at the part of saying that, okay, well, how does the data actually start coming together? Each channel in this case has its own data bucket. I call the fragment of that profile for Sandeep. Okay, this fragment actually exists and it has one primary key associated with it, but any one fragment is a partial understanding of what Sandeep's actual profile looks like. So what is needed is that I need a way to bring all this thing together into a single view. Okay, so first part is that we're separating the picture, saying that there are these fragments where the data resides for this particular consumer. And there are identities, okay? These identities are actually just there across different channels. So now let's look at the next picture, which is how do we actually bring it together? Okay, so once we actually start okay, we're not, okay. Bringing it together, as you start thinking about it, all these identities are getting related to each other, okay? Identity relationship with each other, you can think about something like I'm forming a graph of these identities. This is the identity graph. This needs to be built. Now, once you build the identity graph, that actually tells the profile how to bring together fragments. These are logically brought together. They're not physically brought together, which means that as the graph evolves, as things change, you can actually start bringing together profiles. And now I have a one single view of this particular consumer. Sandeep's profile is actually underserved from a given use case perspective. Now, if you start thinking about what is happening behind this, because you're bringing these identities together, every enterprise needs to start thinking about how to bring this together. And if you want to understand your consumer well, which is the imperative for the experience era, then you must understand the identities. You must bring it together. This is almost balance sheet worthy, actually, asset that any enterprise can build. And this is becoming extremely important. And we are noticing every customer of Adobe actually is looking at saying, how does identities actually work in this new world? Now, let's take to now we know how the profile comes together. Let's look at the next level of details on the profile architecture. So this is essentially just a conceptual view of now how the profile is going to start coming together. From the left-hand side, I'm showing the profile fragments. Okay, the profile fragments is what I talked about, a single-minded view of saying that a single identity gives you a single part of data. So web will have its own container of data. Every interactional event collected from the web will be sitting in that container. Mobile will have similar, same thing. All the CRM data will be sitting inside one container. These containers essentially bring together the data using the identity. Okay, an identity graph that we stitch together, we will bring together all the data on the profile. That becomes the story of saying, I got a unified view of the profile. This actually starts falling under the governance controls. And now I need to start talking about what use cases I'm going to start supporting on top of this. Okay, so as we start looking at the use cases part of it, simple use cases is I need to provide point lookup. Point lookup is needed in many use cases, which is starting with simple like customer support applications, or any high touch application needs to see the customer's profile as the simplest part of it. Even data science workspace or any data science or modeling exercise time to run need to see it. User interfaces need to kind of look at a point lookup. Point lookup means that on the fly, figure out what the graphs are going to come together like, as well figure out what the different fragments are and put together a view of a person at that point in time. Okay, so it's a very complicated query, although it looks like a simple point lookup. Okay, next part is that batch segmentation. Batch segmentation means running a large number of queries on a periodic basis. Number of queries that actually run against this kind of a database actually gets into, for a single enterprise, into tens of thousands of queries actually run. And that is run in a batch model, which means that you're running on a periodic basis. But in the modern world, they also need to be run in a streaming world. Okay, real-time world. Now here where the application starts getting very stringent, you have less than 100 milliseconds to run queries. So for an incoming single event, okay, you have to look up this profile, which is a complex query, and run 10,000 plus queries against all this data set, okay, and actually materialize the query results. You have about 100 milliseconds, and this is for one event. Typical enterprise actually will get hundreds of thousands of events actually arriving every single second. So think about the database load characteristics that they're trying to create in this one. You have hundreds of thousands of events. For each event, 10,000 queries actually need to be run. And the multiplication of 2 is the workload in terms of query execution needs to be run on top of this particular system. Now, these kind of scales, when you're looking at it, of course, one has to get to some of the fundamentals in computer science, saying query execution in a standard model, such as like you're running simply Spark, okay, running a SQL and window-based queries. That's not actually a workable model. You can't run 10,000 queries per second across 100,000 events, each one arriving and actually give 100 milliseconds. So there's a lot of work that is done at some base level understanding of saying how query execution can be modulated and completely changing the tack from some either SQL-oriented query execution or even text search-oriented query execution to a different world we call the query indexing technologies. Okay, now all these things together along with the underlying database allows us now to start to get to saying that we can actually start supporting scale. Okay, now given this much of a background information on what is happening, let's look at the next level of details on the architecture. So now we're going to start looking at the architecture of profile as well as identity. So this particular architecture, as you're starting to look at, has been divided into two different parts: streaming world as well as batch world. There's a lot of similarities between profile and identity, as you will start noticing. From the left-hand side, as I was talking about, there is essentially data that is actually coming into the system. The data that comes is from the interactional systems. typically real-time data collection, we call the data collection service DCS. This is a box where all the data actually arrives. This is streaming data collections. Now, once the data actually starts arriving, we are using Apache Flink and actually trying to do streaming graph compute on top of this. Aided by Redis, Redis is being used as more like a cache that is needed for some other computation. But the results of all this information means we are continuously making updates into Cosmos DB, where actually the graph will be stored. Similarly, from the batch, you have ETL processes that are actually running. Incoming data is actually transformed, laid down into Azure Data Lake. These are essentially Parquet files where we are actually laying down the data. On top of that, we are running Spark-based graph compute jobs. These graph compute jobs essentially are computing as the data arrives, and the data gets again put into graph updates into Cosmos DB. So this entire use case starts looking like Cosmos DB being used for graph computation and running graph API on top of it. And we'll look at the scale at which these systems are actually running. Once you have a graph compute that is actually in place, the next layer of this one actually starts looking at the APIs that are actually supported. As I mentioned, the entire system has been built as API first system. So APIs are continuously accessing, and you have to understand that level of scale at which the APIs are to run is that a graph lookup has to happen every single time that I'm either running a query, okay, or I'm actually doing a point lookup, or I'm running a batch segmentation jobs. I need to do lookups on the Cosmos DB, which is the graph needs to be looked up. So the scale at which these runs are extremely heavy on Cosmos DB, and we're running actually at fairly large scale. I'll show you some of the numbers and the scales at which systems are running. This data eventually then gets used by Unified Profile, and this is where the overall view construction of the profile actually starts. Let's look at also corresponding to the next slide, the architecture of a profile. Very similar looking architecture on two sides, and the symmetry is natural here if you start thinking about it, because the data that is going into profile, the data that is going into identity, they are kind of same data sets. They're really not different data sets that are going to different places. The purpose and the computations that they do on the same data set is very different from each other. So what goes into the underlying data store is very different. So in case of profile, again, at the top level, you have same data collection happening through DCS, the data collection service. Underlying, we are, of course, using Kafka-based pipeline, and this is where the actual ingestion happens. Now, in case of profile, however, every event that actually happens in user's history is recorded and stored in the profile. Okay, so every web visit you make, everything that you do inside your in-app, everything that happens in the store, that information is recorded for that enterprise in their consumer profile. And essentially, we call this as a time series data. So if you start looking at it, the transactions here as that incoming data maps into an ETL conversion happens, and that data essentially goes into UPS. A single event will result into multiple updates happening or multiple transactions that are happening against Cosmos. We'll look at the scale. Okay, the batch ingestion actually has a little bit more complexities because you're running an entire ETL pipeline. You're talking to catalog services. Then the data gets laid down to Azure Data Lake, which is Parquet files. We run compute jobs on top of that, which is based on Spark. You can see again the symmetry there. Similar things are happening on both sides. This is where batch hydration actually happens. We use the term hydration to mean load data into the profile. It's a pipeline and there's a profile, so you're just hydrating the profile. That's the terminology we use. Once the data is actually in the profile, this is where the next set of workloads starts coming into play. The workloads here are essentially about, as I talked about, a periodic query execution, what we call the baseline segmentation or the batch segmentation jobs that are actually running. Streaming segmentation, this is this extreme heavy load that are running every single second with a very high influx of events. And then once this data is actually continuously computed, you're computing audience sets, audience membership, audience payloads, getting them ready for the experience business part of it, which is ready for the applications. And these applications, you have essentially APIs. Again, this system is based on a microservices API kind of architecture. And the export jobs essentially provide data for taking care of operational workloads as well as analytical workloads. Because remember, another thing that this particular database now has to take care of, which is the stitching component that we're putting together one single view of customer, is important even in the insights world, which is where reporting, query processing, data science, etc. is playing, and they need this particular view to be continuously exported. So we are also not only hydrating on one end, we are also on the continuous end exporting the data. And this is, again, one of the speaker was talking about CDCs. System heavily internally uses CDCs to kind of keep on hydrating the data on the outbound side into data lake on a continuous basis, while at the same time ingesting data. Let's look at now the scale characteristics of the system. So before that, let's look at the tech stack itself. As one of the speakers again said, we are not a .NET kind of shop. We are again a Java, Scala kind of a shop. And it has been perfectly fine working with Azure as well as Cosmos DB. No problem of working with Java and Scala. Everything has been actually wonderful all along. Our processing, essentially, we're using Spark, Databricks, as well as the AWS EMR for the legacy reasons. Apache Flink actually is getting used. I showed you a couple of places. Clouds, we are dominantly, actually, most of the structure that I actually kind of showed you here is based on Azure. For the legacy reasons, we still have a lot of AWS presence. We're using all the Kubernetes stack. And the database side, Cosmos DB gets used majorly. The flavors we are using is not Cassandra or Mongo today. We are straight away using the native Cosmos DB, and there is we are finding actually the scale with which is running as well as the reliability that is provided has been enormous for us. Postgres Redis does get used quite a bit for smaller applications. Redis is mostly being the cache kind of applications. Now let's look at the scale actually at which the systems are running. So these are the scales as our customers, enterprise customers, are seeing. Okay, these are not the scales at which the Cosmos DB transactions run. Individual events here result into large number of transactions against the Cosmos DB, and there's a multiplier effect that actually comes into play. Typically, the incoming streaming ingestion today runs at about 7.5 billion events. We have 2.5 billion events actually that are getting ingested on a continuous basis. This results into graph updates. Graph updates is a very complex actually computation, as well large number of transactions and updates that happen against the database. And today, the graph database is a relatively small database, about 40 terabytes with 11 billion essentially clusters and 30 billion identities. Now, let's look at the similar scale exactly going towards the profile. So on the next slide, we show essentially the scale for profile. Now, ingestion events, as you can see, is exactly the same. The number is not going to change from looking at the profile. However, storage scale-wise, we're looking at a single account has a 200 terabytes of data actually sitting in the system with almost 5,000 plus partitions. There are 12.5 billion profiles actually located across 600 terabytes of data. We are actually handling 50 billion point lookups in a given day. Okay, we are actually handling peak loads for a single enterprise in excess of 400,000 requests per second. At this rate, we are running queries against the system. So this has been a great kind of exercise for us to work with Microsoft. I just want to kind of conclude here right now. Just let's look at some of this presentation and information. I've not been able to get into details, but there's a lot of publications and blogs available. I'm reachable at LinkedIn here, as well as some of these blogs are actually available on Adobe site. And any of you are interested in actually seeing more details behind this, because there are a lot of subjects I briefly just touched upon, but I would be happy to get into details. But I want to stop there for any questions.
Thank you, Sandeep. It was really amazing to drill down into Adobe's infrastructure and understand with your help how Adobe is running that infrastructure at scale. We have one question from one of our viewers asking, how did Cosmos DB's specific characteristics help in building this unified view that you have just described?
The specific characteristics, I mean, I will tell you from our simple operational aspect, we were looking at essentially database as a service. Instant scalability was extremely important portion for us. So I just want to talk about what kind of scalability patterns that we see when a bad job actually basically starts. So let's say I have an email campaign or a burst mode campaign that needs to run. The system is running at actually for that enterprise at a scale 0, literally no transactions happening with respect to query processing. And then instantly for next 3 minutes, I need to pump 10 million a minute actually emails. And each email, that number may look small, but each email requires several lookups, several transactions and changes that are happening in the database. And you are moving from the 0 to extreme scales at an extremely fast rate. So think about this kind of workloads, which is dynamic characteristics of the workloads are actually continuously changing. We needed a scale characteristics that can actually move so fast based on how things are actually coming in. I talked about this aspect where we have a continuous load that comes in. Now that's a stable load. When I say few 100,000 hits per second that is actually arriving, this is the data that's getting actually ingested and stored. Again, large number of transactions continuously running. So stable load characteristics, managing that extremely well, right? Then, as I talked about, the other aspect that is important for us is that the underlying architecture itself is the architecture of the system is based on this notion of fragments and the graphs and how the data comes together. It's not a SQL-oriented architecture, right? Although we run queries that look like more or less a straight SQL, we are actually doing joins and all kinds of time series data processing. The underlying data layer had to be done in a very different manner. And that actually required us a document-oriented kind of thinking. So many different flavors that Cosmos DB supports became extremely important for us. Then the partitioning structure underneath. I mean, I talked about saying that we have 5,000 partitions for one single customer. This ability to kind of actually dynamically scale up the RUs and get to a point saying, I can lay down my RUs. And we think in this way, which is, I need ability to run, let's say, 1 terabyte a minute IO against the entire system in a scan job. Ability to get there becomes very important. Now, this particular thing may look very simple, a scan job at 1 terabyte a minute. However, with HDFS, it was not possible to get there. There were initial trials we did. So I think there were many of these considerations that actually kind of started getting us towards using Cosmos DB. And this was early in 2017, 2018, but has been a very wonderful journey for us.
That makes sense. I think it's just mind-blowing to understand at which scale you are operating your whole platform and how Cosmos DB fits into that platform. Thanks again, Sandeep, for joining the conference today. Thanks for taking the time to share all of that very precious information with us. Next, and just before we switch to our next speaker, we have a quick video to show you and Tim has more details.
Thank you.
So Cosmos
Achieve incredible speeds at any scale and keep your costs low with a well-planned
Awesome. Cool. I'll give a quick intro to the video before we dive into it. I guess you got a little bit of a sneak preview there. So as a horizontally partitioned NoSQL database, Cosmos DB allows customers to enjoy the same performance and scale and latency SLAs, whether their database is, megabytes in size, gigabytes in size, or petabytes in size. However, to get this kind of performance, you must take care when picking your partitioning strategy for your data. In other words, when picking your partition key. So let's take a look at this quick video that helps explain some of the considerations that you should take when deciding a partitioning strategy for your data.
Achieve incredible speeds at any scale and keep your costs low with a well-planned partitioning strategy on Azure Cosmos DB. Partitioning involves writing data to servers in a way that optimizes both reads and writes. It's important for all applications, but becomes critical the more you scale as data spreads to more servers. Azure Cosmos DB stores data in virtual buckets called logical partitions. It relies on a partition key to determine which of these buckets to put new data in and where to look for data during a query. When choosing a key, start by testing your most important requests against the following 3 guidelines. 1. Find the write balance. Test your partition key to see how it distributes writes. The goal is to avoid hotspots and rate limits by achieving even distribution of storage and throughput across logical partitions. 2. Aim for a single partition query. Look to see how many partitions get hit when you run your most frequent queries. Ideally, you want to avoid the cost and latency of involving multiple partitions by choosing a key that queries a single partition. 3. Understand cross-partition query trade-offs. If you do run cross-partition queries for less important workloads every once in a while, it won't impact your overall experience. But if it's more than that, you can use an array of discrete values for the partition keys in your query to target a subset of partitions. Looking to unlock the scale and performance of Azure Cosmos DB? Remember, it's all about the partition key.
What a great video. I think we often say that choosing a good partition key is key to getting really good performance when using Cosmos DB. And we'll be hearing more about these concepts later in the session and other live streams. So up next, excited to introduce Alicia. who's a Microsoft MVP and Kafka evangelist at Confluent, to tell us how to stream data into Azure Cosmos DB with Confluent. Welcome, Alicia.
Hi, thank you for having me. Hi, my name is Alicia Moniz, and I'm a Microsoft MVP, as well as a Kafka and Azure Evangelista here at Confluent. So here at Confluent, I empower and educate our team and our customers on Azure capabilities. And within the Microsoft community, I provide helpful tips and tricks for accelerating Azure projects with Kafka. One of my first opportunities here at Confluent was the opportunity to work directly with not only our engineering team, but also the Microsoft team with developing the Cosmos DB Kafka connector. So this was a very fun project for me. On our side, I worked with Nathan Nam, our senior product manager, and Rankesh Kumar, who leads our partner integrations. And on the Microsoft side, I worked with Ryan Crocker and Brandy Brown from Microsoft Commercial Services. I also had the opportunity to work with Siva Mulapudi from development. And if you're interested, Siva and I have a blog out there with some helpful hints on getting connected. And also Ryan was a guest on the Confluent podcast streaming audio with Confluent developer advocate Tim Berglund. So it was really great for me to see the developers on global teams collaborating so seamlessly. And that's been my experience so far working with both Confluent and Microsoft. So thank you everyone for being so welcoming. In January of this year, Confluent announced their partnership with Microsoft, as well as integration capabilities with Azure. So Azure customers are now able to purchase Confluent Cloud via the Azure Marketplace and authenticate to Confluent Cloud using single sign-on. So additionally, users will be able to draw down on their Azure commits, and they'll be able to view their Confluent Cloud resources via the portal. So Microsoft has been fantastic, and they've truly partnered with us on getting this portal integration in place. Special thanks to Ramya Araganti and her team. And they've done a lot of work with putting additional tips and tricks out on the Microsoft Docs site. There's also dedicated space there, and we're part of the partner solutions. So keep an eye out, and we'll be sure to share information as we go through the year with helpful references between our two websites. So customers with Kafka on premises are looking to migrate to the cloud or develop Azure native services. So they usually follow a journey that often starts with data migration, then progresses to hybrid cloud, followed by Azure native app development. So today I'll be sharing the reference architecture and design pattern for a solution integration with Confluent, Azure, and Cosmos DB. So hopefully this will illustrate how Confluent can expedite delivery on Azure projects. This is what a hybrid design pattern with Confluent Cloud looks like. Confluent most likely already exists within your customer's organization and is being used on premises. So developers are using Kafka connectors to ingest data from mainframe systems. Now, the Confluent platform easily allows for the extension of that on-prem data pipeline to the cloud. So step one in Azure projects for most enterprise clients usually involves some type of data or server migration. Confluent can easily accelerate delivery on database migration and consolidation projects with their ecosystem and collection of connectors. So in this scenario, not only do our connectors provide access to open source systems, but we can also easily flow data from multi-cloud sources. This real-time access to data alleviates the pressure of having to move infrastructure prior to building cloud-native applications. On the sync side, the Confluent team has done excellent work in connecting to the popular Azure services, such as Azure ADLS, Blob Storage, and Azure SQL. The Cosmos DB connector is now in beta, but is fully supported by Microsoft. Now, you may be wondering, what is a connector? Connectors are distributed bits of Java code that sit on Kafka clusters. They allow us to import and export data from systems. A managed connector will run on a Confluent Cloud cluster. So scaling and throughput is going to be managed for the user. Now, a self-managed connector will run on a cluster where infrastructure is configured and maintained by the user. While you can communicate with storage, databases, and IoT services on Azure via connectors, you can also interact with Kafka data in Azure App Services by leveraging Kafka APIs with languages such as Java, Python, or .NET. Today, I'll be sharing a walkthrough of configuring a managed Azure Data Lake Storage connector, as well as the Cosmos DB self-managed connector. So I've already configured a Kafka cluster on the cloud. And in the diagram below, we can see that Confluent Cloud is readily available without installation on Azure. We have components such as Schema Registry, KSQL DB, and a variety of managed connectors available for use, with dynamic scaling already handled by Confluent clusters. So on the left-hand side of the diagram are the Azure Container Service components. We'll be installing one instance of the Confluent Control Center and one instance of Confluent Connect. So our script will automatically install the library files for the Azure Cosmos DB connector onto the Connect instance within Azure Container Services. And we'll be able to monitor our services via the Confluent Control Center. To get started, we'll need an account on Azure, Azure CLI tools, and Docker Desktop. Our Getting Started script is available on GitHub. If you'd like to follow along, you can go ahead and clone our repository there. And within the repo is also a sample.env file with our configurations, and of course, our YAML file. Once we're ready, we'll need 5 Docker commands to get up and running. Now, before we get started, let's take a quick look at our .env file. So this file is going to contain the variables that will be referenced by our Docker Compose file. So all I'm going to do is drop this into the project folder that Docker is utilizing. So of course, we'll need to include our Azure account details such as location, subscription, and resource group. And then we'll go ahead and add in information for our cluster. We'll need to provide the cluster bootstrap server information. So whether that's on-prem or in the cloud, we are using a Confluent Cloud cluster. So we'll go ahead and put that URL info there. We'll also need to include the API key and secret. And because we're using Confluent Cloud, we're also going to be using Schema Registry on the cloud. So we'll go ahead and add in the URL info for that, as well as the credentials. Now, to help you get up and running quickly, we're going to go ahead and use code readily available in the Confluent's GitHub repo. So we've set up a separate directory, Confluent Azure examples, and that directory is maintained by my associate, Gianluca Natali, and he is fantastic. He's an associate of mine in Partner Solutions, and he's prepared a quick start to help you get started. He's also got some information out there about integrating with Databricks, and as we continue working with different solutions on the Azure stack, we'll be adding to that directory. Now, we're ready to jump into our demo. First, we're going to walk through creating a managed connector on Confluent Cloud so that we can see how easy it is to interact with the interface there. Then we'll jump into creating the Cosmos DB connector on a self-managed instance. So at the end of this demo, we'll have Confluent Cloud on 2 containers. And one container is going to have Control Center, and one container is going to have the Connect instance. In this demo, we'll go ahead and get started with creating a managed connector for Azure Data Lake Storage. Now, Azure Data Lake Storage is a managed connector, so we can go ahead and create this directly in the Confluent Cloud interface. We can see the tile here for Data Lake Storage, so we'll go ahead and select that. I've already got a topic configured for the demo. So we'll select our topic. A quick rename. The expected values are going to be in JSON. I've also copied out the API key and credentials for my Kafka cluster. If you haven't already done so, you can also generate this API key and secret directly from the connector creation UI. I'm going to go ahead and default it to the topics directory. I've also gone into the settings configuration for my storage account, and I'll go ahead and add in my storage account name as well as the access key that is needed to authenticate to my storage account. My output messages are also going to be in JSON format. My time interval is the time frequency that I'll be partitioning my data. I'll go ahead and select hourly just so that I can more easily debug the initial set of data. I'll go ahead and flush by default 1,000 records. And I'll go ahead and set this to one task for this connector. The connector configuration's been validated and I'm good to go. And we can see that we have the new connector in the provisioning state where it's keying up one task. Now we can go into our storage account, open up Storage Explorer, then open up our blob container, and after our time interval has passed, in this case, 1 hour, we will see the directory topics, and we will see the partitions for the data that we are passing in via the connector. So we can see how easily we can start taking data that's already sitting within the Kafka ecosystem and share that data and spread that data across systems in Azure that we are trying to build up. And this is something that we can do very, very dynamically. So that was a demo of configuring a managed connector. And now that we have a little bit of exposure to the Confluent Cloud UI and how easy it is to work with there, we can go ahead and start looking at, well, what is it going to take to install a self-managed connector on Azure? And in this case, we're going to be installing the Cosmos DB connector. So Confluent has a fantastic developer community, and there's tons of Docker scripts out there for installing the entire Confluent platform. In this scenario, what we're doing is we're just installing one instance of the Connect and one instance of the Control Center. So we can go ahead and get started with the GitHub documentation for the CP all-in-one repo, and in there you'll find the YAML files to do the full Confluent platform install. But in this instance, what we did was we went ahead and stripped it down so that we have configurations for the control center, configurations for the Connect, and what Kafka wants you to do is it wants you to install the library files for the connectors onto the Connect instance and do a quick bounce. So instead of doing that manually, we have a bash script at the bottom of the file. And this is going to go ahead and pull down all the connectors that we want to install on our Connect instance. So in this case, we're definitely going to want to install the Cosmos DB file. And we are planning on having a repo where by default, we'll just go ahead and provide a file that preloads all the latest Azure service libraries so that people who are wanting to get started on Azure really quickly will have this ability to preload this script and launch it in their subscription. Now, we did go ahead and pull out all the variables from the script. So if we take a quick look at the env file, we'll notice that we're passing in our subscription information, our Bootstrap servers. So this is going to be for our Confluent Cloud instance. So this is our Kafka clusters running on Confluent Cloud. We've got our API keys and our schema registry details as well. And yes, I will be deleting these API keys after this demo. So thank you for my data and security conscious friends out there. I know you guys are looking out for me. So looking at what we have available in our portal, and I've already gone ahead and run this script once just to make sure that we are good to go. So what we should see afterwards is we will see within Azure Container Services one instance of the Connect as well as one instance of the Control Center. And what we're communicating with today is going to be our Cosmos DB instance. And looking at the settings here, we do have a partition key on the field ID. So now that we've taken a look at the components, we can go ahead and get started with the demo. Once our containers are up and running, we can access the control center. Let me get that restarted. Once our containers are up and running, we can access the control center via the IP address listed with port number 9021. Go ahead and drop that into a browser and via the UI, access our Connect instance. Now we can see the Cosmos DB sync connector tile here because we've already installed the libraries needed. If you don't see the sync connector tile, then what you most likely need to do is install the libraries on your Connect instance and, of course, restart Connect. And we're just going to go ahead and walk through these configurations. Now, we are using data from the product inventory topic. The name of my connector is Cosmos DB Demo 3. I've configured it for one task. And I'm using the Avro converter. It's important to note that you will need your Cosmos DB endpoint and connection key. And then we'll go ahead and enter in our Cosmos DB database name, which in this case is Connect Demo, and the topic container map. So what the topic container map is the mapping between your topic, and in this case, we're pulling data from the streaming product inventory topic. And the container within your Cosmos DB where you want the data to be synced to. So in this case, I do have a container called product that sits in the Cosmos DB. which is called Connect Demo. So the topic container map is just that linking between the product inventory topic and the product container within the Cosmos DB. I'm going to go ahead and set Cosmos upsert to false. And these are additional values that you'll need to configure if you're using a schema registry that's cloud hosted. Now, you do need the URL, the username, and the access key. And we'll need to configure these 2 times, 1 time for the value converter and 1 time for the key converter. So good news, we have successfully validated our configurations without any issues. So we can go ahead and download a second connector config file here if we've made changes to the UI that we would like to preserve before we hit go. Or we can continue forward. So let's go ahead and continue forward. And we have now that our connector is running, we can go ahead and take a look at our Cosmos DB instance. Let's go to the product container and do a quick query against items. We see that we now have data flowing in to the items container on Cosmos DB. Congratulations, you've created a sync connector and you're now inserting data into your Cosmos DB instance. So thank you. And as next steps, I'd encourage you to visit Confluent on Microsoft Docs, and also you can join our community or visit our Slack channel or our forum at forum.confluent.io. And you can look for my Kafka and Azure Learning series on YouTube. And Gianluca's, Natalie's repository is at Confluent Inc. at Confluent Azure Examples. And thank you for having me today. It's been a blast, and I love hearing about all the different ways that you can interact with real-time streaming scenarios and Cosmos DB. It's a great fit. Thank you.
Thanks so much for the session, for the demo, and explaining how our customers can connect Cosmos DB and Kafka together using Confluent. Had a couple questions from our viewers here. One of them is, can you tell us more about some of the use cases and scenarios that this new connector has enabled that you've seen?
So the connector just came out as of last month. So I haven't had a lot of field time with it, but we do have a number of people who are looking at getting it into production scenarios in the next month or so. So there are some retail customers, but given that it's just so new, but keep an eye out where we'll be happy to share those success stories moving forward.
That sounds great. We'd be happy to hear that feedback. And just got one more question. We're actually curious to learn more about what was the collaboration like between Confluent and you mentioned group in Microsoft Engineering to develop this connector together.
Yeah, so actually it was a lot quicker than I thought. Like I didn't realize, and I should have known better, but I didn't realize Microsoft could move so quickly, with developing, just because there's so much going on in the ecosystem. And I want to say we initiated calls back and forth between the two teams in, I want to say October. And October, November, and within 4 months, they had they had products out there available for use and in beta and fully verified by somebody on our team. So I think it's great, and I think that it's really Microsoft's ability to respond to customer needs. I think there's a lot of people who are looking to work with Cosmos DB, and a lot of those people are also looking at leveraging the data that they have in Kafka. So I think, to the community, it's like kudos to you guys for providing feedback to the dev teams, because just immediately. So we've also worked with the ADLS team, and the ADLS team also developed their own Kafka connector to be compatible with Confluent, and it's been through the verification process. So it's been great working with the development teams. And when Confluent builds out the managed connectors that are managed on Confluent resources and integrating with Azure services, they work hand in hand with the development teams to optimize the managed service connectors. So it's actually been like a fantastic collaboration, and I'm hoping that we can work through as many of the services as we can. So keep an eye out.
That's awesome to hear. Thanks again, Alicia, for being part of our very first Azure Cosmos DB conference. Next and last but certainly not least, we have another speaker lined up, and this is Lenny Lobel. I'm not even sure if we need to introduce Lenny. He has been around for such a long time. Lenny, a long time MVP. For how long have you been an MVP, Lenny?
It's coming up on a decade now, Thomas.
A decade now. Wow.
Yeah, nice to see you.
Nice to see you too, Lenny. Lenny is also the CTO and founder of Slick Technologies, based out of New York, major contributor for multiple Azure data services, SQL and Cosmos DB included. The topic for today, Lenny, is a topic that I think never gets old, is data partitioning and modeling, right?
Indeed.
Yeah.
All right, well, thank you so much. And it's great to see you all here at our first ever Azure Cosmos DB conference. My name, again, is Lenny Lobel. I'm a data platform MVP. As Thomas mentioned, I've been working with Cosmos DB since the document DB days back in 2014. And I'm here today to talk to you about data modeling and partitioning in Cosmos DB. We all know that partitioning is very critical, so we're going to be talking quite a bit about that. Of course, Cosmos DB is many things. It is horizontally scalable, it is non-relational, and a bunch of other things. We can define it as being globally distributed, multi-model, tunable consistency. There's lots of ways you can describe Cosmos DB, but for the purpose of this session, let's just focus on these two definitions. It is horizontally scalable, and it is non-relational. And drilling into both of those, when we're dealing with Cosmos DB, right, we're dealing with a container. And we interact with one container as a single logical resource for storing documents and retrieving documents. But of course, behind that container, there's a cluster of servers, right, if you will, or physical partitions, for lack of a better term. We'll just think of them as physical machines, just like a box that has storage and CPU processing power. And there's been no real upper limit on the number of servers or physical partitions in a cluster behind a container. And therefore, if you partition your data model properly, there's really no upper limit. You have unlimited storage and unlimited throughput with this model, right? Because each physical partition offers more and more storage and throughput. Right. What was the other term we were going to drill into? Non-relational. And if we think about how we do things in the relational world, where we're dealing with tables and rows, what is it that we love to do more than anything else in this world, right? We love to join these things, right? That's what makes us happy. We like to come up with the perfect normalized data model. We like to craft our entities such that we have primary and foreign keys, giving us a very normalized relational data model. And that's the way things work in the relational world. But of course, in Cosmos DB and in the NoSQL world, we are storing data inside of JSON documents, not rows. And while there's certainly nothing you can store in a row that you can't store in a JSON document, and therefore nothing stopping you from designing a data model where you pretty much treat JSON documents as if they were rows and have references from one related document to another. While you can do that, such a design would break down in Cosmos DB. This would perform very, very poorly. It could be made to work, but it could not be made to work well. And why is that? It ties back to our first definition of being horizontally scalable. And the fact is that any one of these documents can land on any physical partition. And in order to maintain the supreme level of performance, the high performance SLAs and the single digit millisecond reads and writes and all of those guarantees on performance, it's simply not practical or feasible to enforce relational constraints between related documents, or indeed to even support joins on them. And that's why we need to think about things differently. Because of course, after that opening, it certainly begs the question, well, then is Cosmos DB at all suitable for a relational workload? And the answer is, of course it is. Otherwise, the session would be very short. It would end here and I would go home. But in fact, many workloads are relational, not all. But many are, and Cosmos DB is certainly suitable for those relational workloads. It's just that you have to think about things differently. You can't do things the way that you've become accustomed to doing them in the relational world, even if some of those tried and true practices have been around with us for decades for some of us. We have to kind of go against the grain of what we consider to be best practices in the relational world in order to materialize relationships in an efficient manner in this non-relational world of Cosmos DB. And so with that kind of backdrop set, let's just have a look at this, this little diagram here. This is our web store relational model. Think of this as a database behind our customer-facing e-commerce website. And it's a relational workload, like a mini AdventureWorks. It's got all the things you would expect to find in a typical relational data model. We've got customers with a one-to-many relationship with their addresses, a one-to-one relationship with their password. We've got products, which participates in a parent-child relationship with product category as well. There are product tags, in which case we've got a many-to-many relationship here. So there's that intermediate table, right? This intermediate product tags table here. Just trying to get my laser pointer to work, right? With foreign keys pointing to both sides of the many-to-many relationship. And we've got sales orders, right? Which are children to customers. So a customer will have a set of sales orders. Each sales order will have a set of sales order details. And it's a small data model, but it is fairly representative of the most common data modeling patterns that you'll find in a relational database. So if you're coming to Cosmos DB fresh and you're just, and it's new to you, your first instinct might be to say, hey, I've got 9 tables here. Maybe I should have 9 containers, right? One container would make sense to store, to think of a table as a container when you're first entering the world of Cosmos DB. But the question is this a good design? And of course, the answer is no, as I started explaining, that due to the lack of joins and the fact that there is no referential integrity and there are no relational constraints, this could be made to work, but could not be made to work well. It would perform very, very poorly. It would be actually the worst possible design that you could come up with. So for the rest of the session, we're going to take it step by step and see how to implement a data model like this in Cosmos DB for high efficiency, high performance, and high scale. And we'll start with customers. We've got 3 tables here for the customers, the one-to-many between customer and addresses, and the one-to-one between customer and password. Step 1 is you just literally translate your column names to property names as if it were a JSON document, which is all I've done here. Other than camel casing the identifiers, the property names in my JSON document match the column names in my database. I had to rename the primary key columns simply as ID because, of course, in Cosmos DB, that ID property must always be named ID. But otherwise, it's a simple translation forward. And at that point, I could stop there, right? Because I do have these kind of, and I don't want to use the word relationships here. Let's just say references. I mean, I do have IDs pointing from one document to another. But let's just call them references, not relationships, because this is a non-relational data model. And so it begs the question, would it be better, perhaps, since we are working with JSON, and JSON is a semi-structured document format, we could embed our addresses as an array, as I've done here. I only have space to show one address, but those square brackets mean I could have any number of addresses, or let's say a reasonable number of addresses, as we'll get to in a moment. And the password itself is embedded as an object using a curly brace. And thereby, you eliminate the problem of no joins if you pre-join, right? We have pre-joined effectively our addresses with the customers and the password of the customer. And we've also solved the problem of referential integrity because the child array lives nested within its parent and can never be broken from its parent, right? So the question is this appropriate to do this? So do you embed or like so, or do you reference like so? And you need to, this is a very typical question that you'll ask during this process. So the rules aren't hard and fast, but the general rules are, if you've got a one-to-one relationship like we have in the case of a password, or a one-to-few relationship like you have in the case of addresses, then it would be reasonable to embed. What is one-to-few? If in the relational world, there's no such thing. It's either one-to-one or it's one-to-many. And even if it's two or more, it's considered one-to-many. In this world, we are thinking of a data model where we have a JSON document with an upper limit size of 2 megabytes, where it's perfectly reasonable to cap the number of addresses that a customer might have in their profile to all fit in 2 megabytes. And so it would make, that's a one-to-few. Think of their orders. We want to think of orders as one-to-many, don't we? We want lots and lots of orders, ideally an unbounded number of orders. And so it's certainly not feasible to embed all of that in a single document. And so then you'll reference. When it's a one-to-many relationship, particularly unbounded relationships, you'll go with referencing. Or if you have a many-to-many relationship, as you'll see the way we'll handle the product tags relationship, you'll also want to reference, or actually a combination of embedding and referencing. And another kind of general rule is that, even if it's just one-to-one, and even if it's or just one-to-few, if you're never really querying for these things together and you're never really updating them together, it also makes sense to reference them. If they're being queried or updated independently. But again, these aren't hard and fast rules, but for our scenario here, we can certainly go with embedding for the addresses and for the password and turn 3 tables into 1, essentially, by encapsulating all of that information in our customer entity. And then the question at that point becomes, if we're going to store customer documents like so inside of a customer container, how do we partition that container? What is our partition key? The most critical question that you'll always have to ask when defining a container. Well, the way that you come up with the right partition key is you need to really understand the most common querying patterns. You need to understand how your application is going to most frequently query your data, how your users are going to most frequently query your data. And again, sticking with this scenario of a customer-facing e-commerce website, the most common query is that a customer is going to want to retrieve information about their profile information, which is their name, address, all their addresses, their password, perhaps for rendering on a profile page. And so the most common query is really to get an individual customer by their ID, which would pull in their addresses, right, because they're embedded, and their password because it's embedded, right? And so that really means the ID property itself would be actually the most suitable property for the partition key here. Now, it might seem like a strange choice because, as you may or may not know, every document is unique in a container based on a combination of this ID property here and whatever other property you decide to choose for the partition key. However, if you choose the ID property itself as the partition key, then you get exact uniqueness of 1 document per logical partition, and you can't have more. Now, again, it might seem like an odd pattern, but it is actually a very good approach when you're dealing with point operations, point reads and point writes, where your primary use case is to read or write an individual document at a time. The ID property is often a very good choice, and it certainly satisfies our most common query, so that's what we'll go with. Now, let's plow ahead with our next entity in the data model, which is product categories. This is very, very simple. It is really just a key value pair, right? There's a product category ID and a display name. So, like before, we translate our column names into JSON property names, and then decide to put that in a container for the product category. We'll put that in the product category container, ask the same question, how do we partition it? Answer it the same way. What's your most common querying pattern? On that website, you're going to want to display all the product categories, right? Maybe in a sidebar on the left or a little menu, so that the user can click a product category to drill in when they find a category of interest to see the products in that category. And that really means a select all. And the way that you implement this type of pattern in Cosmos DB is to add a type property. Really, I want all of them inside 1 logical partition. think of this as a lookup list. Anything that's of reasonable size, and when I say reasonable size, I mean it'll fit inside of a single logical partition, which is limited to 20 gigabytes in size. And we certainly don't have a list of product categories coming anywhere near that. So there's no problem at all putting them all inside one single logical partition. And the way we do this is we add a type property, which is certainly optional. It's schema free. You're free to define any schema. The ID property is the only required property. But it's always a good practice to throw in that type property to help unambiguously distinguish one type of document from another. And if you create a property called type and you set the value of that property to category for every product category document, and then partition on the type property, of course, that's going to lump all of them into one logical partition and give you a very efficient result, a very efficient query that results in returning all of the categories that you have in the database, all in a single partition query. Product tags, I won't rehash that because it's the same concept. A simple key value pair where the user might want to see a list of tags. When they see a tag of interest, they'll want to see all the properties associated with that tag. Same concept. Translate the column names to property names. Put them in a tag container, ask yourself how to partition it, and answer it with the same answer. We want to get all the product tags. It's a select statement that returns them all. So we'll add that type property only for the tag documents. We'll set the value to tag, right? And then by partitioning on the type property, all of the product tag documents are stored together in the same logical partition, just like categories. Products is where it gets more interesting. With products, we have that many-to-many relationship, right? So first we'll do step one, we'll translate our column names to property names. But what about this many-to-many relationship with product tags? The way this is implemented, and I mentioned this earlier, is with a combination of embedding and referencing. I am embedding an array of tag IDs into the product document, but that array itself is an array of references to tags. And in this case, I am embedding an array of tag IDs into each product document. This could also be made to work by embedding an array of product IDs in each tag document. Depending on your usage patterns, one of those may be better than the other, but in either case, this is how you implement a many-to-many relationship. Now, how do we partition the products? Sticking with our e-commerce website scenario, the user has found a category of interest. They want to get all the products in that category. So the most common query for products is going to be get all the products within a given category, not all the products in the entire database. So that means we want all of our product documents to be kind of grouped together logically in a logical partition by category, which you guessed it. If you were thinking category ID is the proper property to use here, you guessed correctly, and that will achieve just that. So now I've got my product documents in hand. But if you look at a product document, what do you have inside of a product document? You have a bunch of IDs, but you don't really have everything that you need to display the product on your web page, right? You have the category ID, but not the category name. And you have the tag IDs, but not the tag names, right? And that means that if you want to get all the products in a given category and display them on your web page, you would have to run one query to get all the products in a given category. This would be fairly efficient because it's a single partition query. You could even further filter on this within a category if you wanted, and it would still be a single partition query, but you don't have the display names. So it would be a second query now on the category container by the category ID to get the display name for the category, and then it gets worse because for each product returned by that first query, you would need to run this third query on the tag document to get the display names for the tags. And this is where, you pound your fists on the table and say, well, where are my joins? Of course, in the relational world, this is a no-brainer. You just join these things together on the IDs and you get the display names, but we're in Cosmos DB world. There are no joins. We need a new way, a different way of handling this. And that is going to be done with denormalization. We're going to simply copy or duplicate that master data in each product document. So each product document, in addition to having the category ID, will have a copy of that category name. That's a copy of the master data. The tags property is now not just an array of IDs, but an array of objects that includes both the tag ID and a copy of the tag name, again, from the master data. So at the point of insert, when I create a new product, I'm also copying that master data for the category name and the tag names, which is great, meaning when I have a product document in hand, I have everything I need to display my product on the web page. But of course, the obvious question becomes, what happens when there's a change to that master data? Somebody comes along and changes a category name or a tag name. And so what we really want to do is listen for changes on those two containers and cascade them to the product container. And that's where the change feed comes in, which is a very critical component of Cosmos DB, a bit of the unsung hero. You don't hear enough about it, but it's what drives a lot of microservice architectures The change feed gives you a persistent log of changes. So every time a document is added or modified or changed in the container, it gets emitted through the change feed in near real time, and also persisted to the change feed, so it can always be rewound and replayed. And you can build microservices. You can use Azure functions to do this very easily, to watch the change feed, respond to every change that occurs, and respond and process it in some way. And in this case, it would be to keep our denormalized data model in sync with master data as it changes. So on the product category container and on the product tag container, they each have a change feed. And when any master data changes, we can have an Azure function wake up and cascade the change to the product table. Here's just some pseudo code. Here's my Azure function name. The Cosmos DB trigger attribute means the Azure function will wake up whenever there's a change to the collection name, which is the container name. That's the product category right here. That's this guy right here on the left that we're watching for changes for, this product category container. And we're handed a read-only list of documents that have changed, and we simply iterate them. And for each one of these represents a change, let's say to a product category. In this case, we will just get the category ID and name, and now we'll need to update each product to cascade and propagate that master data change. And that's done first by querying for all the products in that category very efficiently, again, because we're partitioned on the category ID. So this will return all of the products in one efficient single partition query, and then set up our iterator to process those results and update them one at a time, replacing them with point-right updates. That takes us to our last set of tables in our data model, which is our sales order and sales order details. By now, the process should seem a little bit familiar to you. Step 1, translate column names to JSON property names. Step 2, ask the question, embed or reference. Is this one to many or one to few? Well, hopefully our sales orders are large, but I still think that at 2 megabytes, we can accommodate even a large sales order. So we would definitely be better off by embedding the details. Right, so we'll embed the sales order details, essentially pre-joining them. And they're embedded there as an array of details inside each sales order document. And then we're going to put them in another container called the sales order container. Ask the usual question, how do I partition this container? Well, answer by re-asking the usual questions. What are my most common queries? Well, we've got this very common query, again, that the customer is going to be running. All the customers visiting your website are going to be frequently asking to see their sales orders. And then perhaps less common query that might occur, let's say, in the back office by some executive who's looking at a dashboard, perhaps, who wants to see their best customers, might want to query for all the customers, descending by order count to get their best customers at the top of the list. So let's go with the common scenario first. Getting all sales order for a customer, it would look like something like so. That means that's how the query would look, right? Give me all the orders where the customer ID matches this customer. So if we partition on the customer ID, it'll do just that, right? It'll put all the sales orders for customer A in its own logical partition and each other customer in their own separate logical partitions. I could get all the sales orders or a subset of the sales orders from a customer with a very efficient single partition query. So that means customer ID is the correct, is the appropriate partition key to use here. But now let's slam on the brakes here and pause. And remember, I promised we'd come back to the customer container where we partitioned on the ID property, because that's the same value that we're partitioning on. We're partitioning on the customer ID in both cases. In the case of the customer container and in the case of this sales order container, we determine that customer ID is the appropriate value. Now, granted, it's called ID in the customer document, and it's called customer ID in the sales order document, and we'll iron out that wrinkle in just a moment, but the value is the same. It's the same value that we want to partition on. And when you want to, when your partitioning needs are the same between 2 different types of document types, you will not create 2 different containers. We are in a schema-free world here at Cosmos DB. There's no rules on schema. There's nothing preventing you from storing 2 different entity types in the same container. And in fact, it's encouraged to do so when you have 2 types, even though they're different types, when they share the same partitioning needs or they share similar throughput needs. Those are reasons for storing multiple items of the same type in the same container. And that applies here because we have the similar partitioning needs on both these entities. And that's the customer ID. So what we'll do is we will not create that new sales order container. We will stick with the single customer container that we started with. We'll just have to make a minor adjustment since the ID property in each of these two types is different. In the case of the customer document, the ID is the customer ID. In the case of the sales order document, the ID is the sales order ID. And it's the customer ID property that's kind of a foreign key, if you will. So we'll fix that with another tiny little bit of denormalization. We'll throw in a customer ID property on the customer document and essentially store, two copies. I guess I didn't have that call out in there. We will store two copies of the customer ID. The customer ID will be stored both here and here. And it's the same name property now in both documents. And so I can partition on the customer ID property. It's definitely, I mentioned, a good idea to always have a type property, but that's especially true when you are combining types in a single container. You want to unambiguously distinguish between two types, especially when they're in the same container. But now that's our data model. At this point, we now have logical partitions where we're mixing types. One document in the logical partition for customer is the customer document, which, remember, embedded inside of that are the addresses and the password. And all the other documents are sales order documents, and remember that embedded within those are all the sales order details, and all of which are contained in a single logical partition per customer. So this is a very nice little design for customers and sales orders. I can run a query like so to get all the sales orders for a given customer by querying on the type property for a given customer. In fact, if I left out the type portion of my query and I just got all of the documents for a given customer, it would give me the customer and all of their sales orders along with all of the embedded information with a very efficient single partition query. And so that therefore we are getting around the issue of there being no relational integrity, no referential integrity, no relational constraints, no joins, because you see it's kind of all joined together for us here, isn't it? Because we've partitioned properly, so our documents kind of join together naturally in an efficient manner through single partition queries. And within those documents, we've got pre-joined embedded data as well. And we've kind of like dealt with these radical differences between the relational world and the non-relational world. And that takes us to our very, very last query example, which is that exec sitting in the back office looking at their dashboard who wants to see their top customers. Again, in the relational world, it's a no-brainer. You just do a select count on that order table, group by customer ID, and you're done. That doesn't work here. So what we'll do is another little bit of denormalization. We'll throw in a new column called a new property called sales order count. And we're going to maintain, we're going to not duplicate data in the sense that we're going to duplicate the count. So if there are three sales order documents here for this customer, then the number 3 will be stored in the customer document as well. And that means that if I want to add a new sales order for customer A, I also need to update that customer document to increment the sales order count. How can we do that? If you're thinking change feed, you're definitely on one right track. Change feed is a wonderful mechanism, but in this case, I'm going to do one better because everything is in the same logical partition. We can take advantage of transactions using a stored procedure. Now, this is in this case, it's a stored procedure with JavaScript. It can be done in C# or other languages, I think at least in C# using transactional the transactional batch feature. But in either case, what we're doing here is just a little bit of code that is going to retrieve the customer document, increment the sales order count of that customer document, and then replace it, although that replacement occurs in the context of a transaction and is not actually committed until this JavaScript code completes successfully. So it's been written to the container but not committed. And then we can create the new sales order document and return, let's say, the new count because we want to return something, but only then when the function completes successfully does everything get committed, the new order is written, and the customer document is updated all at the same time. And once you've got that store procedure in place, it does mean that anytime you want to add an order document, you must do so by calling the store procedure and not by just dropping it in by directly inserting it. And if you follow those guidelines, you will always be able to run a very efficient query like so, relatively efficient query. This is a cross-partition query, right? Because there's no where clause in here. We're ordering by the sales order count descending. Is that evil? It's not evil if it's in the minority of cases, like this one exec sitting in the back office who's hitting refresh on their dashboard once an hour. It is evil if it's the customer-facing website with all of your customers hammering away with cross-partition queries day in and day out. That is when cross-partition queries need to be avoided. But here it's perfectly fine. And it's relatively inexpensive because the sales order count has been pre-materialized for us. So to wrap up, with 2 minutes to go, our final design, we have a database with these 4 containers, not 9 containers, 4 containers. And in the customer container, we've got 2 different types. And in the case of customer sales orders and products, we're also embedding to cut down on the number of containers. And if you've been paying attention, and I know you have, you're probably thinking to yourself, product tag and product category, they're both partitioned on type. They're both small lookup lists. Doesn't make sense to create a container per small lookup list. We could combine those into one, let's say, metadata container called product meta, and combine product tag and product category documents, and now bring it down to 3 containers with a very efficient data model to handle a relational data scenario in a non-relational database like Cosmos DB. The key takeaways for this session are: you really must know your key patterns, your key access patterns, how your database is going to be most frequently queried and written to as well, and you design for those patterns. To state the obvious, partitioning is critical. You're not going to achieve that performance and scale if you pick a poor partition key. You want uniform distribution as much as possible, both for storage and throughput. Using these techniques that I covered to materialize relationships either by embedding or by referencing through denormalization, pre-aggregating, combining multiple entities, different entity types in the same container if they share similar partitioning needs and they share similar throughput needs, and using your choice of either the change feed or transactional integrity when the updates are within a single logical partition using stored procedures as well. So I hope you enjoyed the session as much as I enjoyed preparing it for you. I want to thank the team for inviting me to speak to you today, and throw it back to you guys for questions if you have any.
Thanks, Lenny. This was an awesome session. I really love the way you graphically lay out those design considerations. It makes it so much easier to understand, how to tackle those kind of exercises.
I had some good inspiration there, Thomas.
Yeah, well, you presented very, very well, and I hope this is going to help any of our viewers who will need to tackle such a design exercise in the future. We are at time and we are short on time again, but I just wanted to relay one question we got from the many questions we got on the chat. One of our viewers was asking, should multiple microservices use the same Cosmos DB container?
Should multiple microservices use the same Cosmos DB container? So that's an explosive question. You can open Pandora's box with this. I kept things very simple here. Sometimes you can't just settle on one partition key, and you'll need a microservice to actually replicate data from one container to another. Just because you have heavy querying patterns where half the time one property is suitable as the partition key, the other half the time another property is suitable as the partition key, then you're going to have one microservice whose purpose in life is to just keep those 2 containers in sync. And then you will almost certainly need or want to create materialized views for queries that would otherwise be very expensive. And that involves more microservices to create materialized views in yet other containers. So you are talking about multiple containers and multiple microservices. So although all those microservices could all be consuming the change feed of a single container, which is a really nice design aspect to the way microservices can be implemented. You can have a microservices architecture where you've got microservices that are completely independent from one another. They're all sharing the same change. They're consuming the same change feed and maintaining state independently of one another, regardless. So it's a mix. It's a mix and match. It'll depend on your scenario, but it'll almost always involve multiple containers and multiple microservices.
That makes sense. Thanks again, Lenny. We couldn't have our first Cosmos DB conference without you, so we really appreciate your participation here.
Of course. And thanks again, everyone, so much for tuning in. So it's been a really great live stream. It's always great to see how our customers, our partners, and our community are building their applications with Cosmos DB. Just wanted to check in, Tim and Thomas. Did you have any interesting takeaways or insights or things that you wanted to share that you've learned from what we saw today?
Tim?
I really enjoyed Lenny's session. That was awesome. I mean, as somebody kind of who knows a lot about Cosmos DB, it was great to see a lot of tips and tricks that even more advanced users could really use to kind of become a power user of the product. But thank you for watching today. It was really great to have you as viewers. In addition to these great sessions in our live stream, we have 18 on-demand sessions that you can watch at any time. So to see this great lineup of on-demand sessions, you can visit cosmos.com and click on on-demand sessions. You can also join us for a weekly podcast where our host Mark Brown will meet with members of the Cosmos DB team each week and talk about things relating to Cosmos DB, like querying, change feed, analytics, anything you can do with Cosmos DB we'll cover on the show. For the show schedule and upcoming episodes, also you can go to cosmos.com/TV and you'll be able to view all of that there. And finally, if you're new to Cosmos DB and want to find new ways that you can try it for free, read our blog post on the 4 ways that you can try Cosmos DB for free. That'll be available at aka.ms/cosmosdb-free. You can catch our next stream for the Pacific time zones starting in 8 hours. That'll be at 8 p.m. Pacific time and 11 p.m. US Eastern time. And thank you again for joining. It was so great to have you with us for the first part of the Cosmos DB conference.
Thank you all.